Hi.
Hello.
There's a fancy view.
Hello. I can't hear you very well.
Can you hear me? Can you hear me? Hello? Hello, can you hear me?
Oh, yes. Hello.
Hello. Professor.
Hi. Yes.
Hi, nice to see you online.
Yeah, it's good to see you again.
You can hear me clearly?
The voice is kind of small from my end.
So let's try to fine-tune the voice, the volume. So would you like to share your slides?
Oh, okay. Okay. Can you see the slide?
Yes. And you want to check yeah, I can also see the yeah, I can also see the pointer.
Okay, good. Yeah.
主要是这个的说明。OK。
Yes.
Is it later?
It's louder, but there's some echo.
那这样对，还是靠这个那。但是它好像要靠很近，就他说音量有点小。哦。就是可能要对着，对他讲，要这样对着讲。
对着电脑，对他切着电，接着电脑，然后做跟他讲。
好，因为我觉得对着这个讲都很近的话，应该是可以。如果是听众的话，
对，
甚至
还要台前。
对，可能要
对。那我们那个 chair 讲话应该听得到。
可能要超版字。我刚才想站在这边，还是有点显示。
哦，真的。
这个本身没有音量可以放。
这个没有。
OK，那可能就是可能要靠得很近。
对，靠很近。
Okay, if I try this way, this should be better.
Oh, yeah, that's much better. Yeah, I can hear you clearly.
Okay, so this is the optimal way we can do.
Yeah, I can understand you.
So, okay, so if people want to ask questions, you probably need to come and use, just speak like this way.
Okay.
So it's your summer break also?
Mm-hmm. Yes, yeah.
Okay, nice.
Can you see the pointer in the slide?
Yes.
Okay, good. Yeah.
Maybe you want to switch to the next slide. Let's see if we can. Yeah, good.
Okay.
There's no time difference between. So you are in Korea?
Oh no, I'm in Canada right now.
Oh, you're in Canada. Oh, I see. Oh, there's a huge time difference.
Yeah,
12
12 hours.
Yeah, okay. So what time is it now?
It's 9 p.m.
Ah, okay, okay. Not too bad.
Yeah, not too bad. Yeah.
Yeah, okay. Thank you. So maybe we should start.
Yeah, so then we can start. So let's start this morning session on our third day of the summer school. So the first talk in the morning, we have Professor Songsi Lee from Perimeter Institute. He's an expert in field theories applications in condensed matter physics. So today he's going to tell us about non-Fermi liquid theories. So let's welcome Professor Lee.
Okay. Thank you for the invitation, and my apology for not being able to come in person. But I will be happy to engage with people. If you can reach me at this email, you can arrange for a private discussion over Zoom. So let me know. So today I will talk about theories for non-Fermi liquids. So after some brief introduction, main topic of the talk is effective field theories for unconventional metals called non-Fermi liquid, and I will discuss some examples of non-Fermi liquid with hot Fermi surface, and if time permits, I will also discuss about hotspot theory. Okay, so in quantum condensed matter physics, we can crudely classify different phases of matter in terms of the number of entropy that captures the number of low energy number of low energy degrees freedom. So in trivial insulator, there's a unique ground state separated by a non-zero gap. So therefore, at low temperature, lower than the gap size, there's no low energy degrees freedom, and entropy density is exponentially suppressed in temperature, where L is the system size, linear system size, and D is the space dimension, T is the temperature, and delta is the gap. In topological states, although the bulk excitations are again gapped, so extensive entropy density is exponentially suppressed, you can have some non-zero ground state degeneracy protected by long-range entanglement. In more exotic topological state, where excitations have limited mobility, besides the extensive and exponentially suppressed entropy, you can have a ground state degeneracy that is extensive, smaller than the volume, but still extensive. Now, in critical states, you have gapless excitations in the bulk, and therefore the entropy density scales with powers of temperature instead of exponential suppression. If there's a emergent Lorentz symmetry, then the entropy density scales as T to the D, where D is the space dimension. But in metal, you have infinitely many gapless modes around the Fermi surface. And as a result, you have far more low energy degrees freedom, and accordingly, the entropy density can be much larger than relativistic cases. So that is the main focus of this lecture. So let's first consider better understood examples of metal called Fermi liquid. So suppose first consider non-interacting fermions with some finite density. Then we know the ground state is given by field Fermi C, where the Fermi surface divides the occupied state from unoccupied states. Now, if you turn on electron-electron interaction, of course, these fermions can interact and exchange their momenta, and individual single particle state can change their momentum. However, at low temperature, the phase space for the scattering process is much limited. So this can be understood from the following example. Suppose we create a particle with energy E away from the Fermi surface. Okay? And due to the interaction, that particle can scatter into another momentum state, say with energy E1, by scattering a particle at energy minus E2 below the Fermi surface into an empty unoccupied state outside the Fermi surface at energy E3. Okay, so as far as E1 plus E2 plus E3 is E, energy is conserved and this scattering can occur. However, this E1, E2, E3 being positive number and having to satisfy this constraint, the phase space for the final state become proportional to E square, right? Because you have three positive number with one constraint. So therefore, the phase space goes to 0 as E square. So if the interaction is constant in the low energy limit, the Fermi-Golden rule says that the decay rate from this kind of initial state to the final state is proportional to the volume of the phase space, which goes to 0 as E square. So therefore, even in the presence of interaction, particle created very close to the Fermi surface end up having very long lifetime. It takes very long time for that state to decay into other many-body state. As a result, single particle excitations at low energy remains as a coherent excitation. So if you look at the spectral function as a function of momentum and frequency, so spectral function as a function of frequency measures the probability for electron with the momentum k to have energy omega, right? So if you fix certain k slightly away from the Fermi surface, the spectral function is peaked at certain energy, and there's a finite width due to a non-zero decay rate. But as we saw before, the decay rate goes to 0 as E square. So therefore, if momentum approaches the Fermi surface, on the one hand, the energy approaches 0 linearly in E, but the width goes to 0 much faster than the energy itself. So therefore, these single particle excitations have a long lifetime. And as a result, the many-body eigenstates in the presence of interactions are still labeled by occupation number of some single particle. So therefore, there is a one-to-one correspondence between eigenstate of non-interacting fermion with eigenstate of interacting fermion, okay, at low energies. Okay? And this so-called quasi-particle paradigm has been very powerful in understanding the behavior of metals at low temperature. So because the width of the spectral function becomes smaller and smaller as you approach the Fermi surface. At the Fermi surface, the spectral function takes the form of delta function with some non-zero weight, and specific heat become proportional to temperature as in free Fermi gas, except that the coefficient in front of T linear term is renormalized by interaction, and resistivity is also proportional to T square. However, this quasi-particle paradigm breaks down in certain cases, and usually this unconventional metallic states arises near quantum critical point. So imagine at zero temperature, you tune some parameters like doping or field, external field, or pressure, some non-thermal parameter, okay? And as a function of those parameters, the ground state can change the symmetry. For example, you can have a spontaneous symmetry breaking as you tune those parameters. And if that phase transition driven by this non-thermal parameter is a continuous phase transition, and then you have a quantum critical point, and then around that quantum critical point, people have observed some unconventional metallic states whose behaviors do not agree with Fermi liquid. For example, spectral function no longer have a sharp delta function peak. You instead have some only power law singularity as a function of omega. In other words, even particles created very close to the Fermi surface have a large uncertainty in energy, okay? And you also have anomalous temperature dependence in thermodynamic and transport experimentally. By the way, if you have any question, please stop me anytime and let me know. So what happens at the quantum critical point is the following. So suppose I tune some interaction strength in my Hamiltonian, okay? And suppose in the weak coupling, when interaction V is small, the ground state has the full symmetry of the Hamiltonian, but you can imagine that in the strong coupling region, the ground state breaks the symmetry spontaneously. And if this quantum phase transition is continuous, at the critical point, you have a fluctuating order parameter with infinite correlation length. Okay? And this fluctuating order parameter can be captured by some gapless collective mode. Okay, so order parameter become a dynamical degrees freedom, and usually that order parameter fluctuation is described by some collective bosoning mode, and those collective mode can mediate long-range interaction between electrons. Because they are gapless, they can propagate far in space-time, okay? And such long-range interaction in the Fourier space give rise to interaction that is singular in energy or momentum, okay? So in the presence of such singular interaction that become very large at low energy, the interaction can compensate the suppression by phase space. Okay, as a result, you can give rise. You can have a decay rate that is faster than that is greater than the energy self, right? So if decay rate is greater than the energy, then you no longer view that excitation as a coherent excitation. Okay? And another way of viewing the same physics is that at the quantum critical point, due to the strongly fluctuating order parameter, these electrons are constantly scattered back and forth across different momentum points. As a result, Fermi surface is subject to strong quantum fluctuations. Okay. And our goal is to understand the physics of such metallic state that are strongly coupled with this gapless collective mode. Okay, so how can we try to understand such many-body phases? Well, one can try to start from the microscopic theory. For example, you can start with the Hamiltonian of electrons that are propagating in the presence of potential created by the lattice. And also, those electrons are subject to Coulomb repulsion. And if you need, you can also include lattice vibration. However, it is extremely difficult to solve the Schrödinger equation of Avogadro number of electrons that are interacting with each other. Okay. And furthermore, there's a problem of abundance. In other words, it's not clear whether understanding the many-body wave function of 10 to the 23 electron of one particular material teaches us any general lesson for understanding wider class of compounds. And there are so many different compounds, so it will be depressing if we have to do such hard job for every single materials that we encounter in nature or lab. And there's a theoretical framework that address these problems that I mentioned. And that framework is the low energy effective theory. So the idea is the following. Suppose there are many different compounds where the Hamiltonian, the microscopic Hamiltonian is different. Okay, so different compounds have a different lattice potential. So they have different Hamiltonian, right? Now, typically, the different Hamiltonian have a different energy spectra, okay? However, in many cases, we are only interested in the low energy physics because the temperature and energy scale that we have access and we are interested in our laboratory is typically much smaller than the energy scale in solid, right? In solid, the energy scale is order of electron volt, but the room temperature or the low temperature that we have access in our lab is much smaller than that. So therefore, we are mostly interested in the ground state and the low-lying excitations that are close to the ground state. And then if we focus on the low energy spectra, there's a remarkable simplicity that emerge. First of all, there's a class of microscopic system whose low energy spectra are similar to each other. Okay, although the full energy spectra can be very different. Okay, if you just look at the low energy limit, the spectra looks similar in the sense that many-body eigenstates of one system is in one-to-one correspondence with the second system. Okay, so in that sense, they are similar. Although the size of the gap can be different, but there's a one-to-one correspondence between many-body eigenstate between different systems. If that happens, then we can try to group them. Okay, say this is group 1. And we call that phase 1. And there's a second phase and third phase and so on, okay? And instead of trying to understand the full spectra of individual microscopic Hamiltonian, we can try to understand the properties that are common among different microscopic systems within one phase, okay? And this has advantage of capturing something universal among many different microscopic compounds, okay? So we don't have to study, for this purpose, we don't have to study individual microscopic system one by one, okay? Furthermore, there's a chance that we can understand the low energy physics more accurately or quantitatively without having to understand the entire spectra, okay? Okay. So we can then think about what we call effective Hamiltonian, okay? So effective Hamiltonian is a Hamiltonian that captures the low energy spectrum of each phase faithfully, okay? So it's not the same microscopic Hamiltonian, but it only reproduces the low energy spectrum of each phase. So for example, this could be the energy spectrum of particular compound, okay? This is the energy level of many-body electron, okay? But suppose we are mainly interested in the observable at energy scale mu, which is much smaller than the width of the full spectrum, right? And then we can devise a simpler Hamiltonian, effective Hamiltonian, whose full spectrum can be very different from my target system, yet the spectrum of the effective Hamiltonian is in one-to-one correspondence with the original Hamiltonian, okay? And in general, the degrees freedom of the effective Hamiltonian and symmetry of the effective Hamiltonian do not have to be same as the microscopic degrees freedom or microscopic symmetry, okay? However, there is also a price, okay? We have some advantage of using effective theory, but there's a price that we have to pay. In other words, effective theory is only for the low energy physics, okay? So we don't aim to describe the high energy physics of our microscopic Hamiltonian, okay? So more precisely, the use or the goal of the effective theory is the following. So we want to use effective theory to predict all low energy observables, say at energy scale mu, within error that goes to 0 with some powers of that energy scale mu. More precisely, the powers of the ratio between our energy scale to certain UV cutoff scale, some UV energy scale. Okay, so our effective theory become more and more accurate as we go to lower and lower energy. However, if you look at the high energy observables that are comparable to the cutoff energy scale, then the prediction will be horribly wrong. Okay. However, your theory become more and more accurate as you go to low energy. So that's the goal. And then the effective theory can also come with certain number of parameters. Okay, some coupling. And in general, those couplings have to be, or those parameters have to be fixed from experiments, okay? And the hope is that you can use a small set of experiments to fix the parameters of the effective Hamiltonian, and then using the effective theory, you can predict all other low energy observables, okay? So that's the goal. Okay, so, and the most systematic way of achieving this is the renormalization group flow. Okay, so here, the idea is that you have a many-body system where you have both low energy and high energy degrees freedom. But our interest lies in the behavior of low energy degrees freedom. So what we do is to gradually integrate out or remove the fast degrees freedom and see how the effective theory for the low energy degrees freedom or slow degrees freedom evolve as we gradually lower the energy scale. Okay, so this defines the flow in the space of coupling or in the space of theories. Okay, in general, it's an infinite dimensional space because you can, in principle, consider infinitely many parameters in your Hamiltonian. However, as you go to low energy limit, the renormalization group flow is usually attracted toward a manifold of much lower dimensional parameters. Okay, so that is schematically represented by this plane. It doesn't have to be two-dimensional plane, but some manifold in the space of parameters. And under this coarse graining procedure, the effective theory flows into this manifold, okay? And the parameters that are perpendicular to this manifold, we call them irrelevant parameters in the sense that those parameters vanishes as we go to low energy in some power law fashion. Like as we mentioned, they go to zero as some powers of mu, where mu is the energy scale. Okay. Now within this manifold, you can have so-called marginal direction. So marginal direction means that these are the parameters that labels different fixed point. Okay, so here the fixed point denoted by these points on the red line represent the point that is invariant under coarse graining. Okay, so it's like you integrate out the short distance degrees freedom, and then it modifies the effective theory for the low energy degrees freedom. And then if you look at the resulting low energy theory after rescaling, okay, and then the resulting theory looks just same as before. So if that happens, then we say there's a scale invariance. And then under the scale transformation, the parameters of the theory doesn't change anymore. If this happens, we say there's a fixed point, okay? And in general, you can have some set of fixed point, Okay, so they are denoted by that red line. Okay, and then in general, you can have you can go from one fixed point to another fixed point by changing certain coupling, and that coupling is called the marginal parameter. Okay, so you can view marginal parameter as a parameter that labels different fixed point. And then you also have a relevant parameter. These are the parameters, if added to the fixed point, then they flow away from the fixed point, right? So for example, if you start from this black fixed point, but if you add a little bit of the relevant parameter, then under the coarse gradient transformation, it flows out. So it flows away and it flows into some other fixed point. Okay? And then the point is that in the infinite dimensional space of coupling or parameters, there exists a manifold of relatively small dimension, and then low energy physics is controlled by those parameters. Okay, so if we can fix which point within this manifold, which point my theory flows into as sufficiently low energy, right? And if we fix that in terms of some experimental observable, that amounts to fixing my parameters of my low energy effective theory. And then now using that data, we can predict all other low energy observables, okay? Without having to consider the irrelevant parameters. Okay. So is there any questions so far?
We are okay.
Okay, yeah. So, so now our goal is then to apply this program to metallic phases. But there are some theoretical challenges. The first one is the strong coupling problem. Okay, so in many cases, interesting physics occurs in layered compound, where mostly you can think of the physics within the two-dimensional plane without taking into account the interlayer coupling. So in those two space-dimensional theories, or 2+1 space-time dimensional theory, the coupling usually become stronger and stronger as you go to low energies. Okay? So therefore, usually one have to deal with strongly coupled theory, effective theory at low energies. This strong coupling problem is not unique to metal. It's a very common problem in all low dimensional quantum many-body system. However, there's a sense in which that the strong coupling problem is more severe in metallic states, because in metals you have extended Fermi surface and you have an infinitely many gapless degrees freedom. And as a result, the system is more susceptible to quantum fluctuation. Okay, so as a result, various known control scheme that has been known to work in, say, relativistic field theory break down. Okay, so it's harder to control quantum fluctuations in the IR. Okay, so for example, in relativistic field theory, you may have encountered some 1/n expansion, right? If you increase the number of flavors to a large number, and then in the large n limit, usually some mean field theory become exact, and you can consider 1/n correction systematically. However, in metallic system, such scheme still does not, even in the large n limit, the quantum fluctuations are not fully tamed, and non-form liquid in the large limit still remains as an open problem. So in general, it's much harder to understand the physics of interacting fermion in a controlled way. And eventually, we would like to have non-perturbative tools to understand low energy physics. Okay? So this issue of control is not just for improving the predictions at the quantitative level. It's more about capturing the dynamical principle that emerge at low energy at the qualitative level. Okay, because you can sometimes discover the right qualitative physics or right dynamical principle only when you have understanding with control. Another theoretical challenge that is unique to matter comes from the fact that in matter, the low energy effective theory is an infinite dimensional, is defined in the infinite dimensional space of coupling function instead of coupling constant. Again, this is due to the fact that you have gap least degrees freedom labeled by angle around the Fermi surface. Here I have drawn the Fermi surface in two-dimensional momentum space, right? This is kx, this is ky, and then the circle represents the Fermi surface. And to specify a metallic state, first you have to specify the shape of the Fermi surface, right? So that's kf. The Fermi momentum is a function of angle around the Fermi surface, okay? And then now low energy excitations are defined near the Fermi surface, and you can also specify the kinetic energy of those fermion, how energy increases as the momentum of the fermion deviates away from the Fermi surface by delta, then energy increases at low energy, linearly in delta, and then this Fermi velocity Vf is also a function of theta. It's a function of angle. If you have a collective mode, then the electron, say at angle theta, can observe that collective mode and scatter into a different angle. And then such interaction is also function of angle of those electrons. In principle, coupling at one angle can be different from coupling at another angle. You can also have electron-electron interaction, right? Even when there's no collective mode, electrons can interact among each other, and such electron-electron interaction is a function of angle of incoming electron and angles of the outgoing electron. Okay? So you have to think about space of these functions. Okay? And then under the coarse graining or renormalization group flow, these coupling functions flow. Okay? And then ideally, you'd like to identify the manifold of low energy theory in the space of this coupling function. So historically, because it's very hard to consider coupling function, attempt had been made to simplify the problem by focusing on some small number of patches on the Fermi surface. So for example, suppose I don't want to understand the property of the entire Fermi surface. Suppose I want to understand the property of electron around this point K. And maybe in order to understand the property of electron, say, spectral function of electron at that momentum, maybe I don't have to understand the entire Fermi surface. Maybe I can capture the low energy physics of electron around momentum K by including the information of the Fermi surface near momentum K. And maybe there's another patch on the opposite side of the Fermi surface where the Fermi surface is tangential to each other, then maybe that patch also need to be taken into account, because these fermions can scatter while staying close to the Fermi surface by scattering this fermion here. But maybe coupling between this patch, yellow patch, with this patch may not be important, because for the same momentum transfer, this fermion ends up going far away from the Fermi surface, right? So that is the idea. So from this reasoning, people have tried to understand, say, local properties of the Fermi surface, like spectral function, by considering a small number of patches, okay? However, this patch approach has some limitation. It does not capture observables that are non-local in momentum space. For example, you can have so-called Landau interaction. So Landau interaction is this captures the interaction between, say, electron at momentum K and electron at momentum P. Okay, so even if they are within different patch, they can interact with each other without having a big momentum transfer. Okay, basically this electron is scattered to itself, and this electron can scatter itself without having a big momentum transfer. Thereby, they can still stay close to the Fermi surface at low energy, and such scattering processes can happen and do happen. Okay, and this patch theory doesn't capture such Landau interaction. Another interaction that is important is the pairing interaction. So suppose I have electron at K and minus K, okay? And then, because the total momentum of the electron pair is 0, they can be scattered into anywhere on the Fermi surface with the P and minus P, as far as there's a time reversal symmetry, right? Energy at P is same as energy at minus P. So therefore, you have extended phase space for the pairing interaction. And the patch theory is valid only when this kind of non-local interaction in the momentum space is negligible. However, in priori, it's not clear whether such interactions are negligible or not. So in the presence of strong interpatch coupling, okay, then you have to go beyond the patch theory, okay? And you have to include the entire Fermi surface to understand the low energy physics of metal. Okay, so this motivates us to consider the entire Fermi surface as a whole. Okay, and you want to ideally study the low energy effective theory for the full Fermi surface. Okay, including all the gapless degrees freedom within your effective theory on the equal footing. However, in such a framework, there's one immediate issue. Okay, the issue is comes from the fact that once you include the entire Fermi surface, there is a scale associated with the size of the Fermi surface, right? So Kf is a scale, but this Kf is not a high energy scale. Okay, it's not like the energy cutoff that is associated with a high energy degrees freedom that can be integrated out, because Kf labels the Fermi surface. It is associated with a extensive gapless degrees freedom. So therefore, Kf being a large momentum scale is still low energy scale. Okay. And under coarse graining transformation, this Kf never stops running. It can be understood from the following way. Suppose I have some initial momentum, and then suppose it absorbs some momentum Q carried by some collective mode, okay? And then scattered into another angle. And then the change of the angle of the fermion is proportional to Q over Kf, right? If Q was almost tangential to the Fermi surface, then angle is Q over Kf. That's the kind of maximum angle that fermion can have, the maximum change of the angle that fermion can have. Okay? Now, as we go to low energy, the momentum that, say, bosonic degrees freedom carry becomes smaller. Okay, suppose we lower the energy scale such that the momentum carried by boson becomes smaller by a factor of 1 over b, where b is something that is greater than 1. Okay? Now, angle is a compact variable that runs from 0 to 2 pi. Okay? So if you keep angle to be dimensionless, then under this scale transformation, you end up having this Fermi momentum changing from Kf to B times Kf. So in other words, Fermi momentum grows under scale transformation. Physically, what this means is that, of course, Kf is fixed, right, for a given system. However, what this means is that as we lower the energy scale, the typical momentum scale, say, associated with a bosonic degrees freedom, becomes smaller and smaller. And when you measure the size of the Fermi surface in the unit of that momentum scale, Fermi momentum appears to be bigger and bigger, right? It's like for a given size of the Fermi surface, at high energy, boson can carry this much momentum, right? So then at this temperature scale, I can go around the Fermi surface in 12 steps, right? But for the same Fermi surface at low temperature, typical momentum of the boson become much smaller, like this, right? So it takes more steps to go around the Fermi surface. So in this sense, the Fermi momentum is a relevant parameter. It always grows under the scale transformation. And this is inevitable, okay? So as a result, you don't expect to have scale invariance in the usual sense in metallic state. So if you look at the now RG flow of the coupling function, it takes the following form. So here first, you can consider, you can disentangle the overall scale of the Fermi surface, overall scale of the Fermi momentum. So this Kf is average of Fermi momentum around the angle, right? So that sets the overall scale of the Fermi surface. And then this kappa is a normalized Fermi momentum. It's a dimensionless function, okay, that just set the shape of the Fermi surface, okay? And then you can also have other coupling function like Fermi velocity and electron boson coupling and fermion-fermion coupling function. Now, under coarse grading transformation, the most important thing that we have to take into account in metal is the fact that this Fermi momentum flows to infinite. It keeps growing without stopping, okay? And while Kf grows, of course, other couplings like Fermi momentum, shape, and electron-electron interaction or electron boson coupling, they can be renormalized as well, okay? So they will flow, but at the same time, Kf keep growing. So therefore, in metals, you cannot have real fixed point. There is no fixed point. You can talk about fixed point only modulo rescaling the size of Kf. So in this sense, you can only have a projective fixed point, no true fixed point, okay? So when we talk about metallic fixed point, we talk about the line, okay, to which the theory flows into, okay? So as the theory flows toward the line, you know, Kf keep increasing under scale transformation, and at the same time, other coupling functions take some profile that depends on, in general, Kf. Okay, and you cannot set Kf to infinite because, as I mentioned, Kf is not a high energy scale. So therefore, some low energy observers become singular if you set Kf to infinite from upfront. So therefore, you have to remember the fact that Kf is finite. Nonetheless, in the low energy theory, Kf is not generally decoupled in your RG flow. So there are some physical consequences of this projective nature of metallic fixed point. Here in this, I will just discuss one of them using an example. Okay, so is there any question about this point?
Okay, so maybe let me ask that question. So just to make sure that I understand, can I understand it as like, because I keep zoom in to the phase space close to the Fermi surface, so I feel that, you know, it looks like the Fermi surface, Fermi momentum is keep growing.
Yeah, it's like as you zoom in toward the Fermi surface, the thickness becomes smaller, right?
Yeah.
But the circumference measured in the unit of the thickness goes to infinite. So this is the statement.
Yeah. Okay.
So this is the dimensionless parameter that blows up.
Okay. 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 Thank you.
Mm-hmm.
Sorry, may I ask you a question?
Sure. Yeah.
Yeah. So regarding the flow of the Kf, I noticed there are other approaches, such as the you could fix this Kf when you do the RG, so that the Fermi surface is always fixed.
Okay.
And
good.
Kf doesn't flow.
Yeah.
And I noticed maybe TMLC and collaborators, they have developed such a RG scheme that you fix the Fermi surface.
Yeah. So if you
on the RG.
Yeah, that's right. You can do that. So you can try to fix Kf here. Then you have to assign positive scaling dimension to theta. Okay. So you have to do either one of them. Okay. So if you fix the scaling scheme where Kf fixed, then angular variable acquires positive scaling dimension. And as a result, under the coarse graining transformation, the range of angle increases. Initially, it was from -pi to pi. In the next step of coarse graining, it becomes -3pi to 3pi and so on, right? So essentially, the angular variable, the extent, the range of angular variable increases, and that range plays the same role as kf. So either way, you have some parameter that runs to infinity.
I see.
Yeah.
Okay, thank you.
Mm-hmm. So that's why I say this is not avoidable. This is not a scheme-dependent statement. This is truth in every scheme. Okay, so let me try to explain the consequence of this projective nature of fixed point using a simple example called Ising-Numeric quantum critical metal. Okay, so suppose I have a metal with a four-fold rotation symmetry. You can imagine metallic system in some square lattice, right? Then you have a four-fold rotation symmetry. Now, in the presence of certain interaction, the ground state may spontaneously break the four-fold rotation symmetry into a subgroup, say two-fold symmetry, okay? And it's like nematicity. As a result, the Fermi surface can be deformed either horizontally or vertically, okay? So this deformation can be represented by one real order parameter, okay? Now, if this phase transition is a continuous phase transition, at the critical point, you have a fluctuating order parameter with infinite correlation lengths coupled with electrons. So here, the order parameter just describes some texture of nematicity that is slowly fluctuating both in space and time. And you can imagine electron propagating in the background of fluctuating order parameter. So this is a busy slide, but I just want to show how the theory look. Okay, so this is the effective theory of the Ising-Numeric critical matter. So here, this first term is just the kinetic energy of electron. Okay, now electron, this is the frequency. This is the deviation away from the Fermi surface. This is the angle around the Fermi surface. And then, as I mentioned, at low energy of fermion increases linearly in delta in radial displacement with the angle-dependent Fermi velocity. This is the kinetic energy of the boson. And then the second line is electron-boson coupling, where electron at angle theta absorb boson with momentum q scattered into another angle, right? And then this coupling, this Yukawa coupling, is a function of angle. And then the last line is electron-electron interaction. Okay, this lambda describes two incoming electron at angle. Yeah, let me just draw two electron at certain angle, scatter, and exchange momentum and go into another angle. And in this four fermion coupling, there are two important channels that we have to consider at low energy. So we want both incoming and outgoing fermions to be close to the Fermi surface at low energy, okay? And one channel that is allowed at low energy is this forward scattering, right? So electron at angle theta 1 and theta 2 interact, but basically they go back to its original momentum without changing its momentum. That's the for the scattering. So this two angle here, theta 1, theta 2 is the angle of incoming fermion, and this is outgoing angle, right? So this is one channel. And another important channel is the pairing interaction, right? So here, electron at theta 1 and theta 1 plus pi, both of which are close to the Fermi surface, can scatter to other parts of the Fermi surface with theta 2 and theta 2 plus pi, right? While staying close to the Fermi surface. This is another coupling function that is important. And of course, as I mentioned, the Fermi momentum is most important parameter, which is relevant. Now, this theory becomes strongly coupled in two space dimensions at low energy. So we still don't know how to solve this theory in 2 dimensions. So in order to tame quantum fluctuations, one should introduce some deformation of the theory. As I mentioned, the large n doesn't work. What works is, one scheme that works is dimensional regularization, where you keep the dimension of the Fermi surface to be 1, but enlarge the space dimension. Okay, so you basically embed one-dimensional Fermi surface within some general dimensional momentum space. So that space dimension we use as a tuning parameter. Okay, so now, of course, this is the target theory. It's a strongly coupled. But since we cannot solve it directly, we start from some sort of limit. It turns out that d equal 5/2 is solvable. And then you can use the deviation away from this upper critical dimension, epsilon, as a parameter to organize your quantum correction. And that allows us to solve the theory in the small epsilon limit in a controlled manner. So originally, this has been done within the patch theory, and more recently, we extended this to the entire Fermi surface using a recently developed scheme that allows us to keep track of the renormalization group flow of entire coupling function around the Fermi surface. So let me just summarize what we have learned from this exercise. So turns out that physics is qualitatively different depending on whether you are above or below certain critical dimension called DSC. DSC number, the precise value of DSC is not important. It's somewhere between 2 and 5/2. Okay. So although our goal is to understand the physics and d equal 2, it's useful to understand the first physics between DSC and the upper critical dimension, which is 5/2. Okay. So within this window, there's a stable projective non-Fermi liquid fixed point. Okay. So, and here's the schematic functional RG flow. First of all, the overall scale of the Fermi momentum flows to infinite, as I mentioned. Okay, so in this sense, it's not a true fixed point. It's a projective fixed point. Now, we can look at the flow of other coupling function, like Fermi velocity function and shape function, and four fermion coupling function and electron boson coupling function. Okay. Now, first, let's consider the limit where electron boson coupling is 0. Then we consider this plane. Okay. And this is just a Fermi liquid. Okay. So without the critical boson, you just have electrons subject to some short-range interaction. Here it is, we know that the Fermi liquid fixed points are spanned by three marginal parameters. Okay, so they are shape of the Fermi surface, kappa f, and then the Fermi velocity, Vf, and then the Landau function. Okay, Landau function is the forward scattering amplitude, right? So electron at angle theta 1, theta 2 interact without changing their momenta. And these three functions are marginal parameters. In other words, you can tune shape or Fermi velocity or strength of the forward scatterings, okay, freely. Okay, so you have many different low energy fixed point labeled by these three functions. Now, if you turn on the Yukawa coupling, of course, this Yukawa coupling is strongly relevant, okay, at the Fermi liquid fixed point. So therefore, the RG flows towards some non-zero values of Yukawa coupling. Okay, but in the low energy limit, this RG flow converges to a manifold of non-Fermi liquid fixed point, which has a smaller number of marginal parameters. Okay, it turns out that these non-Fermi liquid fixed points have only two marginal parameters. Only the shape and Fermi velocity are freely tunable within the non-Fermi liquid fixed point. Once you know the shape and Fermi velocity, all other couplings are uniquely fixed, including the lambda function. Okay, so in Fermi liquid, you can have Fermi liquid A and Fermi liquid B with exactly same shape, with exactly same Fermi velocity, but with a different lambda function. Okay, but in non-Fermi liquid, you don't have this freedom. Once you know the shape and Fermi velocity, lambda functions are uniquely fixed at low energy. So in this sense, there are surprisingly fewer non-Fermi liquids than Fermi liquids, even though you have more degrees freedom, right? Even though you have more couplings, there are fewer fixed points. Another difference from Fermi liquid is that in non-Fermi liquid fixed point, the pairing interaction is non-zero. Whereas in Fermi liquid fixed point, the pairing interaction is zero. Okay? So therefore, superconducting fluctuations are intrinsic part of non-Fermi liquids. It's inseparable. Now, if you look at the profile of the pairing interaction, okay, so say for zero central mass momentum, but with a non-zero energy of the Cooper pair, you can, at the fixed point, it's a function of the angle theta 1 and theta 2, right? And also it's a function of the energy scale omega, okay? Sorry, how much time do I have?
Roughly 7 minutes.
Okay, yeah, so let me speed up. So, so this is the profile of the pairing interaction at the fixed point, okay? So first of all, you note that the interaction decays in a power law as the separation of Cooper pair increases in the angular space with some universal critical exponent that you can compute. More importantly, I would like to point out that the overall strength of the this pairing interaction goes to zero as energy goes to zero, especially when this angular separation of Cooper pair is large. So naively, you can say that, oh, therefore, these pairing interactions may be irrelevant as far as this exponent is positive, because as far as delta is positive, in the low frequency limit, this pairing interaction goes to zero. However, this conclusion is premature. Whether certain coupling is relevant or not is determined by their contribution to some physical observable. If those coupling give rise to physical observable that are singular at low energy or low frequency, those coupling are actually not irrelevant. They can be relevant. For example, this four fermion coupling can contribute to the anomalous dimension of some vertex made of some fermioning operator. So see this big circle here represent some vertex, okay? Some composite operators of that involves fermion around the Fermi surface. And suppose two of the external leg are at the antipodal point on the Fermi surface, say theta and theta plus pi. And then this composite operator mix with a composite operator with a different angle through the four fermion coupling, through this pairing interaction, right? So this is what we call operator mixing, right? This composite operator at one angle mixed with a composite operator at another angle under coarse-graining transformation. As a result, the scaling dimension of the composite operator is given by the eigenvalue of this composite operator, where this four fermion coupling plays the role of the operator mixing matrix. Okay. Now, in the S-wave channel, the anomalous dimension is given by the angular integration of the four fermion coupling. And interestingly, the measure of the angular integration is singular, like this, omega to the minus 1 over 2z in the low energy limit. Okay, let me just explain where this comes from. This comes from the following observation. So, so at frequency omega, we have to consider the low energy mode whose energy is less than omega, right? And as a result, the fermions are mainly within the shell, okay, with thickness omega to the 1 over z, where z is the so-called dynamical critical exponent. It's set the relative scaling between q and omega, okay? In relativistic system is 1, but without Lorentz invariance, doesn't have to be 1. Its value is not important for us. And then, because Fermi surface is locally parabolic, okay, if fermions are scattered tangentially, it can have a much larger momentum while staying within the shell. Okay, while staying within the shell, electrons can be scattered much, can absorb much bigger momentum, which is proportional to square root of kf times omega to the 1 over z, right? You can say this just follows from the locally parabolic nature of the Fermi surface. So as a result, through this kind of process where bosons scatter fermion from one angle to another angle, at energy scale omega, typically the boson can change the angle of the Fermi surface by this amount, okay? By basically Q parallel divided by KF, right? Which is this, okay? So as energy scale is lower, the size of the patch within which fermions can mix strongly among each other through exchanging boson become smaller and smaller, okay? And as a result, the full Fermi surface effectively break into many patches whose number scales as 1 over delta theta, okay? Which scales as 1 over kf over omega to the 1 over z, okay? So this factor is basically that factor. It basically count the number of patches that contribute to this kind of process. Okay, so now, even if the four-fermion coupling itself goes to zero in power of energy because of the extended phase space coming from the Fermi surface. This integration, this angular integration, can be singular in the IR, in the low frequency limit. And this happens if delta is less than 1/2 or 1/2. Okay, so here's the thing. When delta is 1/2, naively, you may say, oh, four-fermion coupling is irrelevant because its strength goes to zero as you go to low energy limit. However, this is misleading because the phase space for Cooper pair increases this way. Therefore, the effective coupling that actually contribute to physical observables, such as anomalous dimension, can be IR singular, even if four-fermion coupling itself goes to zero at each angle, because there are contributions from so many different angles. If they add up, their net contribution can be singular. Okay, and therefore, and this happens, we say there's a UV IR mixing because when delta is 1/2 or less than 1/2, then the large angle scattering is no longer negligible. So you have to consider the entire Fermi surface. Okay, and then the low energy physics is singularly affected by this big momentum scale KF. Okay, so some large momentum scale, in that sense UV, controls the low energy IR physics in a singular manner. And then if you go below DSC, and it is this dimension at DSC, this is the critical dimension at which delta hit 1/2. Okay, so this delta, this critical exponent here, is a function of dimension. And near the upper critical dimension, it starts from 1. So there, interpatch coupling is not important. So there, the patch theory is good. But below DSC, the delta becomes small enough that you cannot ignore the interpatch coupling. So you cannot understand the IR physics within patch theory. Okay. Yeah, maybe I will stop here because I think my time is up. Okay, so I talked about the low energy effective theory for non-Fermi liquids. And in 2+1 dimension, we have the strong coupling problem as usual. But more importantly, metallic low energy effective theory has this peculiarity associated with a non-zero Fermi momentum. And as a result, in the strict sense, there's no strict fixed point. The fixed point is defined only modulo rescaling of the Fermi momentum. So it is projective fixed point. And there are interesting non-trivial consequences that arises from this projective nature of the fixed point. And one of them I discussed today is this mismatch between the scaling dimension and its relevancy. Some couplings appears to be irrelevant, okay, in the sense that they have, say, negative scaling dimension. It goes to zero at low frequency. Nonetheless, they can actually be relevant for some physical observable because of the KF that runs to infinite in the IR. Okay, yeah, thank you for your attention. If you have any question, let me know.
Questions? Yeah, I got one question. So in the action you provided, there's an bosonic degree of freedom. Are there collective modes?
Yeah.
So
Ising order parameter, Ising numeric order parameter.
I see. So it depends on the system you are looking at. They can be different, right? So
yeah, that's right. Yeah, that's right. Yeah.
Yeah. Thanks.
For example, it can be gauge field in certain case, or it can be ferromagnetic order parameter, or etc.
I see. Thanks. Questions from online audience? Okay. Yeah. Any question? Okay. So yeah.
Before you talk about larger limit, and you say this is solvable when n go to infinity, and why do we? And if the degree of freedom increase, why don't we expect that the gap-based quantum factors also increase such that the system, the theory breakdown?
Is the question why does 1 over n expand and break down?
If the degree of freedom increase, why don't we expect the gap is more correspondingly increase such that the theory breakdown?
Sorry, I'm not sure if I understood your question correctly.
I mean, we increase the degree of freedom of the field, and why don't the gap is small also increase correspondingly?
Yeah, so I mean, in physical system, the flavor of the fermion is 2, for example, spin up and down, right? Now, because it's this too hard to solve, you can try to solve a theory where there are n flavors. Okay, of course, this is not the same theory, right? But hope is that if you understand the physics for large n, maybe n equal 2 theory may be similar. That is the hope. That's why people think about solving the theory in the large n limit, right? Of course, they are different theory. Ultimately, we want to solve n equal 2 theory. But what I'm saying is that even n equal infinity theory remains unsolved because there are too many gapless degrees freedom around the Fermi surface, okay? And as a result, the theory ends up behaving more like a large n matrix model, like a large n Yang-Mills theory, which we know that even in the large n limit, there's some residual quantum fluctuation that we don't know how to take into account in a controlled manner. This is more technical remark, but intuitively, this difficulty arises due to the fact that you have infinitely many gapless degrees freedom, so they are more, susceptible to small interaction. So yeah.
May I ask you a question?
Mm-hmm.
Yeah, so is it fair and correct to say that the patch scheme, FRG, is particularly useful when we are dealing with the non-trivial topology of the Fermi surface? Namely, if the Fermi surface is just a circle, then we may be able to just do the conventional moment potential RG with isotropic Fermi surface. But if the Fermi surface is like cuprates or say nematic states, then this isotropic RG scheme doesn't work, and therefore this kind of patch scheme RG setting. Is it a fair statement?
I'm not sure. In general, all these couplings and parameters of the theory are angle dependent. Right? So, of course, if there's a rotational symmetry, the symmetry constrains the form of the coupling, right? For example, if there's a full rotational symmetry, then KF and VF is just one number, right? And this fermion coupling depends only on the relative angle, not on the each angle. So there's a fewer parameters But generally, if you don't have full rotation symmetry, as is the case in solid, you have to consider angle dependent parameters, and quantum correction in general. Yeah, so maybe interesting thing that you can contemplate here is in general, the beta functional, for example, as you lower the energy scale, you can ask how the couplings or say Fermi velocity theta change as you lower the energy scale, right? And this is in general functional of all coupling function, not just VF at theta, but in general, it's a functional of all the coupling function, right? It's a functional of KF and V and E and lambda and so on, right? So maybe this is one technical difficulty, and maybe related to what you mentioned, if you have metals with a different with a Fermi surface with different topology, right? If the Fermi surface is not simply connected, if you have multiple Fermi surfaces, then you have to include these parameters for each Fermi surface. Okay, so then that's but I guess the additional complexity that arises from the additional Fermi surface or the simplification that arises from some additional symmetry, I think those are relatively minor compared to the fact that we have to, in any case, consider the flow in the space of coupling functions.
Okay, I see. Thank you.
So what happens if there are multiple Fermi surfaces? Should be the projective fixed point? We either two Fermi surfaces dominant or only one of Fermi surface will dominate the physics at the end.
Where in general, if you have one Fermi surface and if you have another Fermi surface like this, right? And then you have another KF. But still, as at low energy, you only consider the modes that are very close to each Fermi surface, right? And still, you have only one overall parameters that runs to infinity. Okay, maybe the average size of two Fermi surface. And then you have two shape function, right? One function characterizes the shape of the big Fermi surface, second function that characterizes the second Fermi surface. So it's like you still have one parameters that runs to infinity, but you have two shape functions, kappa f theta and kappa prime f theta and vf theta, Fermi velocity for one Fermi surface and vf primes at another Fermi surface, and coupling function, etc. So yeah, but I think it's qualitatively still similar.
I think we are running out of time. So let's thank Professor Sangsi Lee again for his nice talk.
Okay, thank you.
Thank you. So let's take a break and come back at 10:45. Yeah. So thank you, Professor Lee.
Okay, yeah, thank you very much.
Pretty late on your side, so okay. So I should let you go and maybe take a break for. Yeah, thank you very much.
Thank you.
Okay, yeah, thank you. Yeah.
Thank you. Bye bye.
Okay, bye.
Oh, right. Maybe I should double confirm with you. Is that okay? We record your talk?
Yes, absolutely.
Okay.
As long as I can get a copy at the end,
Okay.
it's fine with me.
Great.
Let me know when I should start. It's not quite on the right?
Can you move on? Yeah, we should. Well, we'll start in like 2 minutes.
Yes. All right.
Yeah, it's a pity that sort of invite you too late. But
Yeah,
yeah.
I just spent 2.5 weeks in Asia, and the timing just was not optimal to come again. So maybe
Yeah.
next time.
Yeah, it would be nice. Next time you can come in person.
So how large is the audience?
We have like 50 to 30, like 50
Okay.
something. Yeah.
Mm-hmm.
Hello, Professor Delft.
Hello.
This is Chang Ho.
Yes, hello. Good to see you again.
Yeah, so I'm at home. I'm having a minor cold.
Oh, all right. Hope you get better soon.
Yeah, thank you. And it's our great pleasure to have you here to give a talk online. So next time, we will invite you early so that you could really come here in person.
Yes. No, I'd be delighted to.
Okay.
Okay, so it's about time to start the talk. So it's our pleasure that this time this talk will be given by Professor Jan van Delft in LMU in Munich. So he's a very well-known person in numerical algebra, kind of super expert about that. So it's I also know about he's very good in giving lectures. So it's really nice to have you giving a lecture here. So it's welcome to Professor Jan van Delft's talk.
All right, thank you very much for the warm welcome. Just to double check, I suspect I should speak about an hour and then leave 15 minutes for questions. Is that the plan, or how long is the question?
The overall time would be, 75 minutes. So yeah, including questions. So yeah, roughly 1 hour.
Okay. All right. Yeah, so thank you very much for giving me the chance to talk about the physics of quantum impurity models. I've given a similar talk 2 years ago at a summer school in Jülich. And if you're interested, there's also a write-up that you can find at this link over here. And so I've taken many slides from that presentation, and I've added some more at the end. So my goal is to, apart from showing a few slides about the numerical renormalization group, I want to discuss the physics of quantum impurity models that one is trying to access using this technique. Maybe experienced members of the audience might know some of this. For the newer students, I hope it would be useful to get some intuition for the physics that we're trying to describe. So the topics I will cover are the single impurity Anderson model, how local moments form in metals. Then the Kondo model that talks about spin exchange interaction between localized spins and metals. Then a few slides about the numerical renormalization group. You already heard a talk about that earlier today, so I will be quite brief there. Then I will illustrate the power of NRG by showing you a number of results for the single impurity Anderson model. And towards the end of the talk, I will have one slide about the two-channel Kondo model to indicate more intricate physics that can arise if one increases the number of channels. And then finally, I will have a few slides on more up-to-date applications involving the dynamical mean field theory applied with NRG as an impurity solver applied to Hund metals. So all of the top topics are textbook material, and this here is a current application. And feel free to interrupt me if there are questions. Just start talking. I don't see a list of participants right now, but if you start talking, I can hear you. All right, so by way of introduction, the physics that we are trying to describe with NRG's impurity physics, quantum impurity models, and this field was started by an experimental observation almost 90 years ago now, that if you measure the electrical resistance of magnetic alloys, so metals containing some magnetic impurities, then as a function of temperature, the resistance increases at low temperatures and doesn't flatten off as it does for non-magnetic alloys. This was a puzzle for many years until Kondo explained it based on the so-called Kondo model, which I will describe later in more detail, involving conduction band coupled to local impurities. SD stands for a local impurity operator. And the essential physics is that if electrons can scatter off localized spins in such a way that the local spin flips its direction, then that causes an increase in the resistance at low temperatures, because the spin flip scattering rate turns out to increase, gamma of T increases as temperature is lowered, and therefore the resistance also increases. Now, this was a breakthrough explanation, but it also gave rise to the so-called Kondo problem, as opposed to the Kondo model, because Kondo arrived at this result doing a perturbation computation in the exchange interaction J, describing this exchange coupling between localized spins and conduction electron spins. And this, the leading non-trivial term in the perturbation theory, depended logarithmically on temperature. So D would be some high energy cutoff like a bandwidth, and you find this log D over T dependence, which means that as you lower the temperature, you get a divergence in the logarithmic and the perturbative treatment is no longer relevant or no longer justified. And then after quite some theoretical development, finally it was understood what actually happens, and the result is called the Kondo effect. Namely, at zero temperature, this localized spin is screened into a spin singlet. It captures a spin from the conduction band, and it forms a singlet in such a way which has no spin left, so that if other electrons scatter off that singlet, they don't flip their spin anymore. Again, I wanted to cover this physics and various ramifications thereof in today's talk. And the key breakthrough to really make this numerically solid was Wilson's numerical renormalization group that described the crossover from weak coupling you can treat perturbatively to strong coupling, which gives rise to the spin screening. Now, the first question that one faced back in the 60s, addressed by Anderson, is how can it be that you can get a localized spin within a metal in a conduction band? Why would the spin have two possible states? And he wrote down the famous single impurity Anderson model. A cartoon depiction is shown here. It describes a localized level, typically called ED, whose energy lies below the Fermi surface, but it's prevented from being doubly occupied by having a strong Coulomb interaction, typically called U, that prevents double occupation, or that costs a lot of energy. So that's described by this term U, N up, N down. And this term, it's an interaction term, so this makes the model very challenging to solve. And the spin can hop into this localized electron can hop into the conduction band and back, so the level gets a width typically called delta. So that's and that's described by this hybridization term here. So hopping D electron can become a C electron and vice versa. And to characterize this hopping, one typically considers the hybridization function that fully characterizes how the local spin interacts with the band. And a more compact form is to give it a spectral representation like this. So gamma here would be the imaginary part of delta, and that it can have some generic form. But for toy model purposes today, I will just use this hybridization function as a flat box shape characterized by a height pi, delta over pi and a half bandwidth d. Okay, so this delta is related to this hybridization over here. So in a nutshell, the Anderson model involves a local level hybridizing with a conduction band. And this hybridization is characterized by this hybridization spectrum gamma. Now, to give you some indication how spin flip scattering can arise, I've listed here the local levels, empty, singly occupied, or doubly occupied. And the energies are arranged in such a way that the singly occupied levels are the ones that are favored. But nevertheless, one can have spin flip processes by a second order hopping. So consider a configuration where there's a local spin up. It can hop into the conduction band to leave an empty intermediate state, and then it can hop back into the local level, so that in the end you have a spin flip process that has happened, where the local, leaving a particle hole pair in the band, but the total spin here has flipped. This can also happen in a different way, in that you first get an electron from the conduction band hop into the local level, so you get a doubly occupied level, and then one of those electrons can hop back off. And the net result is that the local spin has flipped, and the particle hole pair has been created in the conduction band. And the effective rate for these processes, computed second order perturbation theory, is given by a constant denoted by J, which depends on the Bayer parameters of the Hamiltonian as shown here. You can estimate it from second order perturbation theory. It counts the coupling constants, hybridization constant squared divided by the energy cost for the intermediate levels. Right, and this turns out to be the effective exchange constant also for the Kondo model. Now, the Kondo model is related to the Anderson model that I've just discussed by projecting out those empty and doubly occupied levels that in the previous slide only occurred as intermediate states anyway. And then one can show that at low energies, low temperatures, low excitation energies, the physics of the Anderson model is equivalently described by the Kondo model, which just involves a conduction band and a local spin coupling to the spin density of the conduction electrons at the site of the local impurity. And the physics of this model just involves spin flip scattering. Electron can come in, scatter off a local impurity, and in the final state, the spin of both of them have flipped. And the calculation that I described a few slides ago, done by Kondo, did perturbation theory in J and found this logarithmic dependence on temperature that described the increase in the scattering rate. So that was the success of Kondo's calculation. Now it turns out one can capture higher order terms in the scattering if you do a so-called poor man's scaling renormalization. And I don't want to go through the details, but just mention the upshot. One can define an effective dimensionless coupling, which is the coupling times the density of states. And due to logarithms of this type, this turns out to be function of temperature, an increasing function of temperature that I indicated over here. So as you lower temperature, this effective coupling constant becomes larger and larger. And from this functional form, you can see that it will diverge when the denominator here is equal to 0. And from that, the temperature at which that happens is called the Kondo temperature. And it's given by this relation. Just equate these two terms. And if you solve for TK, you find that it depends exponentially on the exchange coupling constant. So this is a very interesting phenomenon. It's a dynamically generated energy scale. This scale is not part of the bare parameters of the model. And if J becomes small, it becomes exponentially small. However, when temperatures become of order TK, then this perturbative treatment of Kondo no longer works. Okay. Now, it turns out one can rephrase this coupling constant depending on temperature, this effective dimensionless coupling constant, by just inserting this expression for TK in here. You can express this dimensionless coupling in terms of log of T over TK. This is a nice form because the bare parameters, bandwidth and J, no longer occur explicitly. They only occur through the dependence on TK. That means one has universality. The physics of impurity models depends only on the ratio of some energy scale like temperature over TK. And that means if you do experiments on several different types of impurity materials or magnetic alloys, then you can rescale the results for physical measurements, for example, the resistivity. If you plot them as a function of T over TK, then they all collapse onto a universal curve. This is some experimental data from many years ago. So this Kondo temperature really is extremely important scale in these impurity models. And as I emphasized, it's exponentially small. So that will be a challenge for numerics. All right. Now, as I just said, this effective coupling constant tends to diverge if you compute it perturbatively. So the question arises, what really happens when the temperature goes to 0? If this divergence is just an indication that the way we approach the problem, namely by doing perturbation theory in J, is no longer adequate at 0 temperature. So von Anderson in the end of the 1960s was the first one to realize that what really happens is that the total spin of the system, the spin of the impurity and the conduction band, that is 0 at 0 temperature. And the way this happens is that a spin screening happens. A cloud of conduction electrons with a net spin of 1/2 screens the local spin to form a singlet. And for spin screening, several cartoons have become popular. So one is this one, which depicts local spin and one electron from the conduction band bound into a total spin of 0. It's just a cartoon. Another cartoon is to form this famous spin up, spin down, minus spin down, spin up combination, where it's indicated here that the local spin and the spin from the conduction band are involved here. Or a third cartoon is to try to depict the cloud of conduction electrons around the local spin. They have a typical extent. Xi K is called the Kondo length, goes like 1 over the Kondo temperature. And since the Kondo temperature is exponentially small, this Kondo length is typically very large. So it's a very extended cloud of conduction electron that's involved in the screening. And then the idea is that the spin flip scattering, which at high temperatures can result in the spin flip of an incoming electron as it scatters off the local spin, that is no longer applicable at very low temperatures, because if spin screening has happened, an incoming electron just sees an object with 0 spin, and when it scatters off that, its own spin does not scatter. Okay, a non-trivial thing does happen. It requires a phase shift, and for some applications that's very important, but I will not dwell on that any further. All right, now in the next slide, I want to indicate some physical consequences of spin screening. So how does it manifest itself in observable quantities? And one of them is impurity entropy. So the impurity entropy, very roughly speaking, is just log of the number of local degrees of freedom. And at high temperatures, there are 2 local degrees of the number of local states are 2. The spin can be up or down. Whereas at very low temperatures below the Kondo scale, you have just a single screen singlet, and that implies that the impurity entropy, if you compute it as a function of temperature, decreases from log 2 down to log 1, which is equal to 0. So that I will show you serious computations later. This is a freehand drawing to indicate this crossover. Another quantity of interest is impurity spin susceptibility. So you can get that by computing the local magnetization in a small magnetic field, which tends to polarize impurity, and then asking how does the susceptibility, what's its derivative with respect to field in the limit of 0 field. So if you apply just a very tiny field, how does the spin react? And for a free spin with not embedded in a conduction band, it's known that the susceptibility increases like 1 over T. That's a famous Curie law. And it would diverge when temperature goes to 0. But if you embed it in a conduction band, the spin screening causes the susceptibility to saturate at some fixed value using and an approximation for this dependence is this Curie-Weiss law, which goes like 1 over temperature plus Kondo temperature. So when T is much larger than TK, you get this 1 over T behavior. And when T goes to 0, the result just goes like is inverse proportional to the 0 temperature specific susceptibility, right? So this can be actually used as a definition of TK, computer susceptibility at 0 temperature, and you can extract TK from that. So that's another important manifestation. And the asymptotic behavior at large and low temperatures is known in great detail for the Kondo model. Another important quantity is the electron scattering rate, right? That's what causes this resistivity anomaly. And therefore, temperatures above the Kondo temperature, one gets a logarithmic increase. That's a behavior that Kondo first explained. And then at very low temperatures, spin screening cuts off this logarithmic increase. And it saturates, and the leading deviation from the 0 temperature value depends quadratically on temperature. And also here, the asymptotic behavior and the limit of very low temperature is known exactly and from analytical arguments. And these prefactors, getting them right through a numerical calculation is actually an important consistency check on the numerics. All right, so things to remember is the impurity entropy crosses over from log 2 to log 1. As screening sets in, the susceptibility crosses over from a Curie law to a Pauli behavior, and the scattering rate from a logarithmic temperature dependence to quadratic temperature dependence. All right, so those are by now very well established results. And now I want to turn to the computational challenge of how does one actually compute this? Because as I indicated, standard perturbation theory does not work. There have been other analytical approaches developed over the years, like beta-ansatz, conformal field theory, etc. But they all have their limitations. And the method that is most flexible and powerful, in my opinion, is the numerical normalization group invented by Ken Wilson in the mid-1970s. It's part of his citation for the Nobel Prize that he got for developing normalization group concepts per se. And in that early work, he actually also, apart from conceptualizing the idea of the normalization group, he came up with a concrete numerical implementation for the Kondo model, and that yielded a huge amount of insight. So that's what you heard already earlier today, but let me briefly go through the main ideas. So the Wilson realized that to describe quantum physics properly, he has to be able to resolve this exponentially small scale of the Condor temperature. And therefore, he came up with the following idea. Let's start from the hybridization function that defines the Anderson model. It's indicated schematically in blue here. And this red dot depicts the impurity, and these orange patch here indicates that the impurity couples to all parts of this conduction band via hopping. So it means you can hop into into conduction band energies of any states of any energy. And then Wilson had the very ingenious idea to discretize the conduction band logarithmically. So he just picks a few discrete states that represent the energy interval around them, but he chooses these states to have energies that become exponentially dense around zero. That's his trick for resolving low energy scales. Technically introduces a discretization parameter called lambda, a number bigger than 1, and the discrete energy levels that he chooses here scale like lambda to the minus n, where n would count these levels. So that's this famous logarithmic discretization. And then he showed that one can map the model onto a half-infinite chain, the impurity sitting on one side. And this is just a unitary transformation involving the bath sites. You just take linear combination of states in such a way that the hybridization gets represented by a chain. And the important part of this idea is that the hopping matrix elements, TL, along the chain decrease exponentially as a function of L, the site index. And that means you can solve this chain iteratively. You first take a short chain, let's say the first 3 sites, and diagonalize that system numerically. Then you get a set of energy levels. They are called Wilson shell. Shell is this word for the levels that you find. And it will turn out that you will get very, very many of these energy levels as you increase, as you add more and more sites. So Wilson decided to do a truncation. He discards high-lying states and keeps only low-lying states for the next iteration. Next iteration means you add one more site and compute how this coupling of this new sites to the levels that the kept levels that you already have, how they are affected, and they typically split up. So the spectrum is refined each time you add a coupling, and it's refined because the strength of this coupling is comparatively weak relative to the energy spacing of the shell that you already have. This is due to this energy scale separation or this exponential decay of the coupling rate. And then you continue like this. You again discard high-lying states, add another site, diagonalize, and in this way you get a spectrum that's resolved ever finer and finer as you go along the chain. And then you can, what Wilson realized is that you can extract very interesting information from looking at the behavior of the low-lying states of each shell. So if you, for every iteration, subtract the ground state energy and then rescale that spectrum by multiplying by a factor that scales the average spacing of the lowest lying levels to be comparable. So you multiply by this factor here. Then you get a so-called energy level flow diagram as indicated here. So along the horizontal axis is plotted the characteristic energy scale of each iteration. The early iterations would have large values of lambda, so they're plotted on the right. And as you iterate and resolve the spectrum more and more finely, but rescale at each step, you find a flow of energy levels of this type. So there are regimes, so-called fixed points, where the energies don't really change. But so this would be one fixed point. It's called the free orbital fixed point. That's a regime where the local states of the Anderson model can flip freely from one to the other by hybridization. And then if you lower the energy scale at which you analyze the spectrum, you get another fixed point where the energy levels don't change much. That's called the local moment regime. And what has happened now is charge fluctuations have frozen out. They're no longer noticeable at smaller scales, and you only have two relevant degrees of freedom locally, spin up and spin down. And as you lower the energy even more, spin screening sets in, and you get another crossover and another fixed point, and that can be understood in terms of just electron scattering of this screen singlet. And one of the really remarkable consequences of Wilson's RG idea is that he was able to numerically track the crossover through these three fixed points, from one fixed point to another one numerically. So I think conceptually this was one of the really major breakthroughs, that he found a way to make this idea of a RG fixed point concrete. Now, just to show you what's going on behind the scenes, I borrowed one slide from a talk given this summer by Fabian Kugler, a former coworker of mine at a school in Sherbrooke, which shows what the actual numerical data looks like. So here he shows the actual energy levels for a few iterations in an unscaled form. So you start with a few very coarse levels, and at each iteration, the number of levels increases. In blue, he indicates the states that will be discarded, in black, the ones that will be kept. And you see that one very quickly zooms into very, very low energies. Now, to be able to see what's going on at these very low energies, there are two steps involved. One is you subtract the ground state energy at each level and plot things on a logarithmic scale. Then what's shown over here looks like that. And now it's a log scale. You can see with each iteration, you zoom in more and more. And then the next step is you rescale this by this characteristic energy lambda to the n/2, or I had called it L/2. Then you get this set of levels, then all gets scaled into the same energy interval. And then you get a set of levels shown here in blue, in purple and green are even and odd iterations. And the energy level flow diagram that I showed you in the previous slide, you get by just looking at, let's say, the odd iterations, and then you get a flow like this. So when you see a beautiful plot, sorry, I'm misclicking here, like this. What's behind that is a lot of rescaling, and but the final result can be really nicely uncovers these RG fixed points. All right, now an important step beyond what Wilson did was taken by Anders and Schiller in around 2005. They came up with an idea to utilize the discarded states. Let me just go through this iteration again. So once you've diagonalized this system of L sites, you have your kept and discarded states. But then they say, let's not throw them away. Let's realize that there are also the rest of the chain can be viewed as an environment for the part of the system that I've diagonalized up to this point. So let's give them these states a name, the environmental states, and then you can combine the discarded states with environmental states and collect them, sort of say they describe high energy part of the spectrum. And then at the next iteration, when you've added another site and diagonalized the next Wilson chain, you again take the environment, the states that you've not yet kept track of. Is there a question? Is there a question?
No, I don't think so. So if you don't have a question, you should probably mute your microphone. Right?
All right. So each step, yes. So
如果跑
Um,
到，那如果跑到别
so
的东西，因为它可能有同时可以当喇叭、当麦克风啊，
all right, so
对，
somebody
可以当
should
麦克风
那
嘛。
所以是耳机啊，我现在是要耳机，不是耳麦啊。
mute this person or either
因为
ask a
你的
question
你
that I
现在的
can
这个东西，它
understand.
是一个耳麦，所以它可能抓到这个东西叫耳麦。
All right. So at each iteration,
它就露出来了。
you don't throw away the discarded states. You add them and you collect them. And in this way, and now there's the one approximation that you make is at each iteration you assume that
我昨天听 YouTube 的时候还可以。
the discarded states that you get, combination of the locals of the ones that you've computed and the environment, that the energy that you assign the energy of the Wilson shell states that you've computed at that level, you assign that energy to this set of discarded states. And in this way, one can fully resolve the spectrum and find a so-called basis, complete basis of energy levels. So you can build projectors onto these set of discarded states in such a way that the combination of all these projectors fully resolve the many-body spectrum, the many-body Hilbert space. And I don't want to go into the technical details, but one can show that in this way you can compute spectral functions, so correlation functions involving two operators A and B, and which would have a Lehmann representation of this form. You can resolve them in terms of those projectors and compute them explicitly. And so in this way, one can compute spectral functions or correlation functions and keep track of their energy dependence on all energy scales. All right, so this is as much as I want to say about NRG. And now let's go back to the physics, what can extract from them. So for the symmetric Anderson model, symmetric means the local level is equal to minus U/2. This Condor temperature has an explicit form found by Haldane first. It looks like this. And if you then compute with NRG the impurity spectral function, the impurity entropy, this series of fixed crossovers from between three fixed points, a free orbital, the local moment, and the strong coupling fixed point looks like this. So in the free orbital regime, there are four local levels indicated over here. So the impurity entropy is log 4. Then in the local moment regime, it's log 2. You have to spin up and spin down, and then spin screening sets in. So this is an NRG result showing how screening sets in as you go from high to low energies. Then the impurity spin stability that I had talked about earlier, this crossover from Curie behavior to Pauli behavior looks like this if you compute it with NRG and you plot the results on a log-log scale. Okay, so this comes out really very cleanly. And then one can also compute the dynamic impurity spin stability. So for that, you compute a time-dependent correlator, SC at time 0, SC at time t, commutator of that, compute that as a function of time, and Fourier transform. And that's called the dynamic spin stability. And the imaginary part of this, this quantity has a telltale form. It's plotted over here on a log-log scale for several different temperatures. Let's look at zero temperature, lowest temperature first. It has a maximum roughly at the Kondo scale. So where this quantity peaks, you can read off the Kondo scale from that. At high temperatures, it increases like 1 over omega, and at very low temperatures, it decreases like omega. And then as a function, if you crank up the temperature, then this peak moves to higher temperatures, and the characteristic temperature at which energy at which the peak happens is basically given by temperature. Okay, until the temperature drops below the Kondo temperature, and then those curves all lie on top of each other. So I emphasize this because it will play a role later on again. So from the dynamic spin stability, one can read off the Kondo temperature. Now, there's another very important quantity that's a local spectral function. You get that by computing the a local D-Dagger correlator and then Fourier transforming that. And the imaginary part of that is called the local spectral function A of S, AS of omega. And that has the following very striking features. It has two side bands, the so-called Hubbard side bands, that corresponds to excitation that you can reach by adding an electron to the local level and then paying the energy cost of double occupancy. So this peak is around U/2, or taking out an electron, then paying the energy cost of having an empty side. This peak is at minus U/2. But then in addition, there's this very striking sharp resonance around zero frequency. It's called the Abrikosov-Suhl-Kondo resonance, and it sets in only when the temperature drops below the Kondo temperature. To make more sense of it, it's useful to plot it on a logarithmic scale, and then one sees at zero temperature, the blue curve, this peak sets in when frequency is below TK. But as you increase temperature, this Kondo resonance gets suppressed, and at temperatures well above TK, it disappears completely. So this is a many-body effect resulting from spin screening. My color bars here indicate the energy regimes. So at high energies, one has this free orbital regime where all local charge states can contribute. Then over here, when this logarithm sets in, you have only local spin up and spin down active. And then spin screening is characterized by this very sharp resonance. And it's one of the most impressive features of NRG that it's able to resolve this exponentially small scale in great detail. Now, again, when you see such smooth curves, what's going on behind the scenes is actually one gets a set of discrete delta peaks from NRG, and they have to be broadened. So this is another slide I borrowed from Fabian Kugler. So this smooth curve over here is actually the result of a set of broadened versions of the discrete peaks that one finds from solving this spectrum of this Wilson chain. And another comment to make, while very low energies can be resolved well with NRG, due to this logarithmic discretization, for the same reason, high energies cannot be resolved well. So the side peaks here, or in the previous slide, these Hubbard sidebands, they are typically overbroadened. So with the calculation that is able to resolve high energies better, one would find quite significantly sharper peaks out here. So these broad sidebands, those are the price to pay for being able to resolve the Kondo resonance very accurately. All right, one other quantity of interest is the local self-energy. If you take the local correlator and you express it in the standard form, there would be a hybridization function here, and then what remains is the self-energy. This quantity also has a lot of structure. I mean, its imaginary part typically characterizes the broadening of the local level, or the decay rate of local excitations. And the fact that the Kondo resonance emerges indicates that at low energies, you have well-defined quasi-particles. And that's reflected in the fact that the self-energy plotted here has a dip. It goes all the way to zero, around zero frequency, but in a very narrow energy range. And if you plot this on a log scale, it looks like this. So this drop down to zero that you see here looks like this on a logarithmic scale. You see, as you lower the temperature, the offset at zero frequency decreases all the way down to zero. Okay, so and in a dependence that goes like omega over Kondo temperature square. And actually one can do even better. One can rescale this behavior. It's known analytically. It should go like omega squared plus pi squared t square. The prefactor is also known from analytic arguments. And if you have a really powerful energy implementation like we have in Munich, then you can exactly reproduce this scaling form. Okay, one last comment about behavior of this Kondo resonance. If you apply a local magnetic field that splits the spin up and spin down levels on your local level, that will counteract the formation of this spin singlet. And as a result, the Kondo resonance will split into two sub-resonances. This is NRG data at zero temperature. As you crank up the field, this local resonance splits up into two parts. And that's also something that can be observed experimentally. For example, one realization of the Kondo effect is in transport through quantum dots. So let's say a puddle of charge coupled to a two-dimensional electron gas in the late 1990s, early 2000s. This was a very active field of research. And then one could measure the splitting up of the Kondo resonance by monitoring the conductance through such a quantum dot. All right, so that's what I want to say about spin screening. I hope you get some sense of how it manifests itself physically. Now, let me spend one slide on a more involved model where spin screening does not happen. It's a so-called two-channel Kondo model. You take the local level and you couple it to two separate but identical conduction bands, indicated by this index J, was 1 or 2 here. And then spin screening cannot work. The problem is you have two bands that try to screen the local level. So let's say local spin up tries to capture one electron from one band, but since the model is symmetric, it then also has to capture an electron from the second band. And the net result is an object which again has spin, has a spin 1/2 pointing downwards. And so that again will try to be screened by capturing two spin up electrons, giving you a net local spin up. And that again tries to be screened, so on and so forth. So you never achieve full screening. So this situation is called an overscreened Kondo effect, and it causes non-fermi-liquid behavior. Fermi-liquid behavior was characteristic of this fully screened spin, and by the concept of fermi-liquid indicates that the remaining electrons after spin screening behave just like non-interacting electrons, like a fermi-liquid. But here, this doesn't happen because of this overscreening. And it manifests itself in measurable quantities. For example, the impurity entropy goes from log 2, but never reaches 0, never reaches log 1. It actually reaches log squared of 2. That's a quite remarkable result. It means there's the fact that it's non-zero, that the zero temperature entropy is not 0, indicates that there's still some remnant degree of freedom left inside this overscreen cloud. And another indication for the physical quantity is the impurity susceptibility. Remember, I told you earlier for the usual Kondo model, the so-called fully screened Kondo model, the impurity susceptibility drops down to 0 at 0 frequency, at 0 temperature. But over here, it does not happen. As you lower temperature, it approaches a plateau and stays finite all the way to 0 temperature. So that is a characteristic indication of so-called non-fermi-liquid behavior. It behaves different from the spin screening that I had showed earlier. So there are numerous other ramifications of non-fermi-liquid behavior, and it's been a hot topic for many years. Also in current research on heavy fermions, things like this can be found. So I just wanted to alert you to the fact that spin screening does not always happen. For it to happen, you have to have a balance of degrees of freedom. For every local degree of freedom, you need one conduction band in order to properly screen it. All right, now in the final part of my talk, I want to switch now gears and tell you something about research done during the last 8 years or so. it's a sort of a modern or application of NRG to understand strongly correlated material. They are called Hund metals. I will say a little bit more about how they're defined. And with my group and in collaboration with Gabi Kotler, starting 2015, we've published a number of papers about this topic. I won't go through all of them. I will just discuss spin orbital separation and non-fermi liquid behavior, just to give you an indication of what type of physics one can study if you have a tool like the numerical renormalization group at your disposal. So the Hund metals are wideband metals where you don't have only a local Coulomb interaction on every atomic site. So it's like typically d orbitals, which have strong local Coulomb interaction, but also a so-called Hund's interaction, which tries to align the spins on a local level. So, and one can try to make realistic models for this, but starting around here, 2008, people have studied a toy model. I call it a 3-band Hubbard model with a Hund's coupling. And the idea is on every site, you have an interaction term, which has a local Coulomb interaction U, but then also a term that couples to the total spin squared. And the coupling there is called JH, the Hund coupling. And what this local spin, what this Hund's term likes to do is it likes to align all the electrons sitting on a single orbital, on a single atomic site, so that they point in the same direction. So it favors a large local spin. And this brings an extra, very interesting piece of physics into the game, right? So this S is, this operator is formed by looking at the spin on site I. Si is the spin on site I. You get it by this combination of d dagger sigma is a Pauli matrix. D m sums over all the local orbitals, right? So now you should have in mind on every atomic site you have several orbitals. In this case, in this cartoon, 3 of them. And the Hund's interaction would like for the spins sitting on those orbitals to be aligned, okay? And the Hund physics becomes particularly prominent if you study this with a filling of 2. So you put 2 electrons into these 3 available orbitals. So the filling is 1 away from half filling. And then there's also, apart from the local spin, which if you put 2 electrons there, they would like to form an orbital triplet with total spin 1. There's also an orbital degree of freedom. Namely, you have 3 different ways how to form this local triplet because either one of these 3 levels can remain unoccupied. So the level that's unoccupied, the fact that there are 3 possibilities means there's also an orbital degree of freedom. So this is now a much richer impurity model. It has not only spin degrees of freedom, it also has orbital degrees of freedom, and that gives rise to new physics. Okay, and the way that this has been studied is using dynamical mean field theory. So I will not say much about the method itself, but the idea is as follows. First, you acknowledge that it's not possible to solve a model like this defined on a lattice with interactions on every site. It's not possible to solve that exactly. So what you can do instead is you can single out one lattice site. You treat that as an effective impurity embedded in a bath. The bath describes all the other sites on the lattice. But you do it in such a way that the coupling between the impurity and the bath is determined, the hybridization function is determined in a self-consistent way. All right, so if you pick out this a single site coupled to a bath, the corresponding cartoon would look like this. If you have a 3 orbital model for each of these 3 levels, there's an effective bath coupled to it. The bath describes all the other sides of the lattice, and this hybridization coupling indicated by these shapes here that has to be determined self-consistently. So you end up solving an empirical, and from the local correlation function, you can recompute the hybridization with the conduction band. And if you do that iteration over and over again, eventually you get the self-consistent coupling of this local level to the bath, and that treats the local physics exactly. On the formal level, the assumption that one makes by this approach is that the self-energy is momentum independent, or said differently, purely local. That's certainly an approximation, but depending on which type of physics you want to study, this approximation turns out to be reasonable. If local interactions dominate and the momentum dependence is not important, then you can do pretty well with this. All right, now to get this to work, you need an impurity solver. You need to be able to solve this impurity model, and NRG is the method of choice for us, because with that you will be able to resolve very low energies. And now on the next few slides, I want to give you a glimpse of the type of physics that can emerge from that. All right, so the first quantity that I want to show here is the local spectral function A of omega. So it has an interesting structure as opposed to the condor resonance that I showed you earlier. There are now there's a strong peak around 0 and then another shoulder around here. And that actually is a result of having two different condor peaks superimposed, a narrow condor peak due to spin physics and a broader condor peak causing this shoulder. And the reason for that interpretation follows if you compute the spin susceptibility and the orbital susceptibility. So the spin susceptibility has a broad maximum at the energy scale that one can identify with the condor resonance in the spin sector. So that's why I showed you the spin susceptibility plots earlier. This is a blue curve. And if you compute an analogous quantity for the orbital degrees of freedom, you get the red curve, and it also has a broad maximum, but at the higher energy scale called the orbital condor temperature. And now the important point is that these scales have an energy window between them. And you can associate the width of this narrow peak with the spin condor resonance and this energy scale at which the shoulder emerges with the orbital condor resonance. And the fact that these two energy scales don't overlap, that there's a window between them, as indicated on this plot here. So there's a window between the orbital and the spin condor resonance, means we get a phenomenon called spin orbital separation. It means that orbital degrees of freedom get screened at higher scales than spin degrees of freedom. My cartoon at the bottom is trying to indicate what's going on. So at very high energies, you have your spin 1/2 that can occur in 3 different ways, depending on which of the orbital levels is left free. So there's an orbital degree of freedom. And then as you lower energy, this orbital degree of freedom gets screened. So the impurity captures 1 extra level from the conduction band, gives you an effective spin 3/2. And now there's no orbital degree of freedom left. And the peak in the orbital susceptibility is indicative of the screening effect. But now you still have a spin 3/2 left. And in the second stage of screening, the spin degree of freedom gets screened in that the effective impurity captures 3 spin down electrons from the conduction band and forms a spin singlet. Okay, so you go from spin 1 to spin 3/2 through orbital screening, and then to spin 0 through spin screening. And this energy window between these two processes that manifests itself in the fact that the spectral function get a broad peak on top of which is superimposed a narrow peak. All right, and in this intermediate regime, when excitation energies lie between the spin and the orbital condor temperatures, that's very interesting. That gives rise to non-local, non-Fermi liquid behavior. You can visualize it by saying you have still slow fluctuations of large local moments, these spin 3F guys, whereas the orbital degrees of freedom have already been screened. All right, and now there are many questions that one can address once one has realized this. We published this in 2015 in a paper co-authored by the leading author was Kati Stadler, a PhD student in my group. Once one has realized this, one can ask many questions, and one of them was, can one characterize this intermediate energy regime better? Is there some fixed point in the sense of Wilson that governs this behavior? So that was a question that we tried to address in a PRX appeared in in the year 2020, written by lead author Elias Wart, another PhD student. And the idea that we pursued here, that Gabi Kotler suggested, was maybe we can tune or deform this model in such a way that the energy window between the spin Condor scale and the orbital Condor scale, that this energy window becomes larger. All right, and so here's what Gabi suggested. The local impurity model for this 3-band Hubbard-Hund model, as I said on the previous slide, is an Anderson type impurity model. And if you do a Schrieffer-Wulff transformation to map the Anderson model to an effective Condor model, I mean, the Schrieffer-Wulff transformation is the theoretical tool by which you can recover the low energy effective model from the Anderson type model. If you do this for this impurity model, you find that there are 3 types of couplings. There's an exchange coupling between the local spin and the spin density of the conduction electrons, which I call JSP. But there's also an exchange coupling between an effective orbital degree of freedom and an orbital density of the conduction electrons. And then there's a third one where both the spin and the orbital degrees of freedom couple to a corresponding density in the conduction band. So there are actually 3 types of couplings. And if you just do the Schrieffer-Wulff transformation, all 3 of them play a role, okay? And as a result, it's never possible to crank open this energy window to become very large. But then Gabi suggested, let's treat this effective Condor type model as a model in its own right, and let's not use the couplings that we got through the Schrieffer-Wulff transformation. Let's treat J0, K0, and I0 as independent as independent terms. And then it turns out if you just decrease J0 while keeping K0 fixed and I0 very small, then but you make J0 smaller and smaller, then this window between the spin Condor temperature and the orbital Condor temperature becomes wider and wider. You can crank it open for like 9 orders of magnitude. So you get a very wide window of spin orbital separation. So this is now no longer the impurity model relevant for the initial 3-orbital Hubbard-Hund model, but it's related to it by deformation in parameter space, if you wish. And then interestingly, in this scenario, we were able to characterize the behavior of the impurity stability in great detail. So, okay, technically speaking, what one can picture what happens as you do an RG transformation from the original model. There's an RG flow, and initially, if you start from the Anderson type Hamiltonian, you immediately flow away to a strong coupling fixed point, far away, fully screened fixed point, far away from a non-Fermi liquid fixed point. But if you choose J0, this exchange coupling, to be 0, you flow all the way to a strong coupling fixed point, which has non-Fermi liquid behavior, and that then describes the physics in this energy window. All right, and now just indicate how to understand what's going on there. This orbital screening actually can take place in one of two ways. You can either capture spin up or a spin down. In my previous slide, I said I only focus on this capturing a spin up. And then there's some interplay between these two states, and only at a much lower energy scale does this one win. Okay, and then eventually gets spin screening. And this regime, this intermediate regime, that represents a spin orbital separation window of Hubbard type models. And this one over here, and that we were able to characterize in great detail. We were able to explain certain power laws that one finds in these spin susceptibilities by drawing on a conformal field theory analysis. So these powers, these very weird powers that show up here, can all be explained using conformal field theory arguments. I don't want to dwell on this now. That's a rather technical topic. I just want to indicate that with NRG, one is really able to separate all these energy scales, and with quantitative accuracy for the exponents, we were able to really recover analytical predictions in this regime. All right, so I think it's time to wrap up. Let me summarize. What I tried to describe to you today is first the physics of spin screening for the usual Kondo effect, where the local spin gets screened by conduction electrons. And then in the last part of my talk, I wanted to indicate that this is just one manifestation of a very large class of models involving local impurities coupled to conduction bands. And one can get much more complicated scenarios for screening if you have also orbital degrees of freedom involved. And that physics is actually relevant for real materials. Current frontiers in the application of NRG that I'm involved with and interested in is using DMFT with NRG as an impurity solver for real frequency descriptions of low temperatures of real materials. So today I only talked about toy models, but one can actually design, if you start with a DFT treatment of ab initio treatment of the band structure, and then just focus on those bands that are closest to the Fermi level, one can write down effective impurity models that are realistic and treat them with energy. And Fabian Kugler, in collaboration with Antoine George and other co-workers at CCQ in New York, did some very nice work in this direction. Another frontier is using DMFT plus NRG to study heavy fermion materials, where you have localized electrons hybridizing with conduction electrons in a way that you end up getting very large effective masses. So that's ongoing work, topic for different discussion. And then regarding methodology, improving the methods or developing the methods, some recent highlights is a paper by Fabian Kugler where he showed how to compute the self-energy more accurately than we had all been doing for many years. And something which is really on the high-end application side is how to compute local 4-point functions. So if you have DT-dagger correlators, we recently found a way to compute such objects. Also, that's much more involved, but it can also be done within the framework of NRG. And applications of such 4-point computations would involve, if you want to improve DMFT by including non-local correlations. So if you want to recover the momentum dependence of the self-energy, one of the computational schemes is that you take the DMFT vertex as an input and use then diagrammatic methods to include the momentum dependence. But again, that's a topic for a different talk. So with that, let me close here, and I'm looking forward to hearing your questions.
Thank you very much. Thank you very much. Okay, time for questions.
Can I ask your question?
Yes, please.
Thank you very much for this wonderful talk. I learned a lot. So I have a question regarding the DMFT plus NRG.
Yes.
you mentioned in one of the slides saying that you can sort of map the MFT. Yeah, that's right. That's the slide, right? So could you tell us a little bit more about how you self-consistently solve the Bath and hybridization coupled to the impurity, say, from the original BMFT problem?
All right. So keep this picture in mind of replacing all the other sites except one special site by a bath, right? And now let me go back to my slide about the Anderson model at the very beginning. So if you have a self-consistent impurity model, what you do, you start with some guess for this hybridization function. Let me just activate my pointer again. You start with some guess for this hybridization function. And this model is now supposed to mimic the coupling of impurity to a self-consistent bath. And then you compute with your numerical tools, you compute the local spectral function, what I called A of omega, the thing that had this Kondo resonance. It looks roughly something like this. And then the self-consistent relation says that this local spectral function must be related to the hybridization function. So you use the local spectral function to recompute the hybridization function. And the new hybridization function defines a new impurity model. So it then changes its form a little bit. And then you recompute the local spectral function. So you get another quantity that looks something like this. And you have to iterate it until then the recomputed hybridization function is equal to the one you started from. Okay, so
I see.
I don't have an equation here prepared for the self-consistency loop, but the idea is you put in delta, you compute gamma, and from gamma you recompute delta, and eventually those two must remain unchanged.
Great. Sorry, one minor technical question. So when you do so, you sum over the momentum for the original, Kondo lattice, right?
Yes. Yes.
So the sum over K here, K refers to the momentum of the 2D lattice.
Yes.
I see.
Or the 3D lattice, yeah.
Or 3D.
And that's the point where the band structure of the model enters. Over here, the toy model or the Anderson model, the band structure does not really enter because, formally it looks like it enters here, but in the end, only this quantity gamma of epsilon matters. But when you close the self-consistency loop in NRG, in DMFT, there's a sum where the actual dispersion of the bare lattice enters, and that's where the band structure information comes in.
I see. Great. I got it. Thank you very much.
Sure.
Okay, I also have several questions.
Yes, please.
Maybe for my first technical questions, how do you define temperature in NRG? Yeah, I missed that part.
Okay, that's actually a good question. Let me go forward to my NRG slides. Okay, so temperature enters. Okay, you can do it in two ways. The crude way that Wilson did is he argued when you have these set of Wilson shells, the shell that at a given temperature is most relevant is the shell for which this characteristic level spacing that you've resolved iteratively, when that is comparable to temperature. So when Wilson computed, for example, the impurity entropy, he just took all the discrete levels of that shell whose characteristic energy, this lambda to the minus L over 2, this characteristic energy was equal to temperature, and then computed the entropy with those discrete set of levels. And then for a lower temperature, he used the next shell, and so on and so forth. And he argued that the reason why it's okay to do this is shells who have a level spacing much larger than temperature, most of those energies, excitation energies, are huge compared to temperature, so they would not contribute. The Boltzmann factor for those would be essentially 0. And then shells which have a much smaller energy spacing, those states would not be really resolved in the scale of energy of the temperature. They would just look to be completely degenerate. So he argued just use a shell whose characteristic spacing is equal to energy, is equal to temperature. Now, a more refined way of doing that is to say, well, if you compute expectation values, you always take a trace over the density matrix times some operator, right? And this density matrix you can write as a sum over all eigenstates of your system with Boltzmann factors, e to the minus beta energy. And now with this scheme of Anderson-Schiller with this complete basis, you can really resolve the full many-body Hilbert space. And if you want to now write if you want to write, let's see whether I can do that, whether I can activate my pen. So let's see, if you want to compute the density matrix, you take these projectors, you can view them as a sum over all states that you've computed. So E is the environmental state, S is or alpha I call it here, right? So you have to sum over all energy shells and over all states alpha and over all states energy, over all environmental states. And then over here you add a factor e to the minus beta and the excitation energy that you've computed at Wilson shell L. So you can really write down explicitly the density operator in a complete basis. And since you've computed all these excitation energies along the way, you really have access to this density operator. And this is where the temperature enters.
I see. That makes sense. I have another question is about this overscreening.
Yes.
So that is only possible when you have 2 bands, and I don't quite understand why it cannot happen in a single band case.
So in a single band, the cartoon would be, you have your local level, and it captures 1 electron from the conduction band, and that gives you spin 0. Okay, and then the system is happy. So technically, you want to minimize the contribution of this exchange interaction, and you can couple 2 spin 1/2 to give spin 0. So that's possible. But in this overscreen case, if you just follow my animation, so if you couple 3 spin 1/2, then you can get total spin 1/2 or total spin 3/2. So technically, if you have spin 1/2 times spin 1/2 times spin 1/2, you can either get spin 1/2 or spin 3/2, but not spin 0. And so this whole thing here would be a cartoon representing this effective spin 1/2 that arises. And then you still have a spin 1/2 embedded in a conduction band. So you try to couple it again, to screen it again. So now you again take direct product with 2 more spin 1/2s.
I see.
But again, now you can get 1/2, 3/2, 5/2s, but you don't get spin 0.
I see.
Right?
Yeah, right.
Whereas if you, in the usual Kondo effect, you just have direct product of 2 spin 1/2s. This would be the local spin, and 1 spin from the conduction band. This can give rise spin 0 and spin 1, and this would be your singlet.
I see.
I mean, this is a very cartoonist argument, but it does capture the essence. And if you then do a fancy computation with a method like NRG or conformal field theory or beta ansatz, this intuition gets supported by the actual computations.
I see. I see. Yeah. And maybe last question is about this Hans metal.
Yes.
So just a curiosity that to just follow your cartoon picture, if you measure the spin on this impurity side,
yes,
you find it, first increase then decrease, just to confirm the cartoon picture.
Yeah, let's go to the cartoon. You mean this one?
Yeah. So the total spin on this impurity side, it should first increase, right? And then
That's right.
And then decrease.
Yeah, okay. Let me take the simpler cartoon that I had here at the bottom. So yes, you begin with spin 1. Hund's coupling ensures that it's spin 1. Then screening happens that the local orbital degree of freedom gets screened. So you want to fill this empty level by capturing one electron. And the Hund's coupling says, if you want to capture one, let's capture spin up. So the net result is a spin 3 have effective impurity that has no orbital degree of freedom left. The orbital degree of freedom has been screened. So it goes from spin 1 to spin 3 half. And then in the last stage, it gets fully screened, goes to 0.
Right. And does you see in your simulation, and does it also see in experiment?
Yeah, so in experiment, yes. So it's not easy to directly compute the spectral function in experiment, but you can compute things like, or measure things like spin susceptibilities. And we wrote a paper, I'm not sure I've cited it here, this Nature Communication, that was an attempt to combine ab initio computations with NRG, and there the ab initio computations all with realistic band structures for 2 typical Hund metal materials. We studied their spin susceptibility as a function of temperature and confronted that with NRG computations, and the two seem to be consistent. So and the most direct confrontation between NRG and real material is this paper on strontium ruthenides by Kugler, Singelstrand, etc. So there again, realistic band structures were taken as input, and there are R-based measurements of the local density of states, and one can extract a low energy scale, so-called thermoliquid scale, where the final spin screening sets in. And we were able to accurately predict this crossover scale from ab initio input and then putting a DMRG plus energy, a DMFT plus energy computation on top of that. So I don't think I recall an experimental measurement that directly looks like this. But if you take the model at face value, this definitely comes out. And those experimental quantities that we could describe, they came out properly. You see, if you take a realistic band structure, things are more complicated than what we found here. Then there are the 3 bands are not degenerate. Okay, so the strongest oversimplification of this model is that all 3 of these orbitals are viewed to be degenerate, but in reality there will be crystal field splittings, and there will be the 3 bands that contribute will not have the same bandwidth, and there will be Van Hove singularities and all sorts of real-world complications enter. But one can keep track of them, and we believe that this physics of spin orbital separation and spin screening, orbital screening followed by spin screening, that still plays a role there.
I see. Thank you very much. Do you have more questions? I also have a question.
So for this case, if I start with the one orbital instead of two, how do I understand the evolution? Does the forming of the hybridization between the localized orbital and the itinerary gradually increase from 1 to 3, or it become 3?
So let me just understand your starting point. You want to have still 3 local levels or just 1 local level, or?
Only one. Well, no,
All right.
orbital. And there's one orbital will hybridize with itinerant electron. So in your...
All right.
Yeah, so in...
Yes. But now you want to do that in the context of DMFT, right? So you want one local orbital hybridizing with a lattice of other ones, right? Is this a context that you're asking about?
Yeah. In final, you will hybridize a 3-particle state. I mean, fill up these 3 orbital label.
Okay. So the orbital labels are whether you need them or not depends on the lattice model that you want to study, right? So you have to, when you write down the lattice model, you have to say how many bands you want to treat. So in our case, M goes from 1 to 3. If it's a 3-band model, if it's a just usual Hubbard model, for example, then you would not have this index M. It just have one value, let's say 1, and you would not have this Hund's coupling. And then you also get interesting physics. You get a mod transition, meaning as you increase interaction strength, at small interactions, you will have a metallic phase, and if the interactions become large enough, you get a phase transition, and within DMFT, you get a phase transition to an insulating phase. The way it manifests itself is if you compute this Kondo resonance or this local spectral function. So this would be at small u, let's say t equal to 0. And at large u, then this resonance would just disappear. So there's sort of it will become narrower and narrower as you increase u, and it will just suddenly disappear at an abrupt value. So that's called a mod transition from a metallic state to an insulating state. If I had more time than before discussing this, Hund's physics would have been appropriate to first discuss this physics. This would be the first canonical application of DMFT to give some non-trivial physics is typically to describe this mod transition. But that happens if you just have one local level per site, coupled to other sites that also have one local level, right? And if you have now several local levels, then you have an orbital degree of freedom that comes in, and then story becomes richer. I'm not sure. Did I answer your question?
My question is that can I see gradually the hybridization of electron coming? I mean, if I start with a one orbital, the orbital field in this 3-label system, and the itinerary electron will hybridize with this localized electron, and will they come immediately to a 3-particle state or a 2 from 1 to 3 gradually?
Okay, so your starting point is 3 orbitals.
Yes, 3-orbital label, but only filled with 1 electron.
Oh, I see.
Yeah.
Okay. So then what you're considering is you're filling, you consider a filling of 1. Okay, that means you have to adjust your chemical potential in such a way that there's just 1 electron per level. Then this Hund's coupling does not play a role, right? Because the Hund's coupling only becomes important if you have two or more local electrons that can couple to total spin, right? So if you just have one electron, then the Hund's coupling does not do anything non-trivial. You can still consider it. So it's a well-defined model, and it will also show, it will also, I believe it will also show a mod transition, but it's less rich than if you, the behavior is less rich because Hund's coupling does not play a direct role. It plays an indirect role in if you want to consider virtual transitions, like to an intermediate state, which is doubly occupied, and then electron hops off again. That doubly occupied state, this intermediate state, will feel the Hund's coupling. So there will be some traces of Hund's physics in correlation functions, but it's not as direct as the case of a local filling of two. So did that help to answer your question?
Yeah, I understand. Thank you.
All right.
All right.
Any other questions?
Or questions online for the online people? Okay, if not, we are also a little bit over time, and
Yes.
thank you very much again. So
yeah, all right. Thank you very much. Thank you very much for inviting me, and I wish you a successful continuation of the workshop. Goodbye.
Yeah. Okay. Bye-bye.
Bye-bye.
Bye.
Right. I will come back.
应该会吧？是吧？看一下这个，那就把它查一下。
我是这个 Mac，
那边有好。
这边打左。哦，
只有一个，但下面那边
那边也可以，
啊，对，那边也可以。把反开边。
有二半的，所以还是弄这样。
正下面我帮你看。先够长。
可以。
那我就把它打回来。那我就把它打回来。 把你比较那个。OK，你经常会发。不是。哦，放着放去了。那我对调实测。我说会不会改？我说会。就有理由，我还得去。发生了什么事情？啊，那次有什么？这么可能？你讲过几个？对吧？
哦，对啊，对啊，他已经受已经受那是你看他讲到这市场发展出来东西，但是是那个他们上跟别人，他们现在上他们算高阶的需要算，蓝色跟后的方面，看你跟不同。那这个是为了偏要的。算了。他刚开始可以，他上点东西，对，他配合他的是哪个就是他用什么电子最低的，先挑起跟你上到一起，然后这个地方到正八里头，有点高，我就没上电了，我就再删一个，我就直接就发了，你不这个都测，没好，对，那就对，这个会背起，对，自己背起都会。
然后再哎，那个你去了再关掉，再去，你刚才把它关了，现在线上看不到。怎么会？干回应了。
还是让那个
收到。
他其实他那个他能够追踪他的每一个类型是对到的3类，还有多少？这个是最难算的，就是我算一个看的，我知道那个还是要做的。哦，那你要稍微对，只有对光后，我确定他是不是要做看？这工作上面。
比方说刚才那个张安，因为我们在讲话，然后那个要拿冷静，对，那所以现在讲话的人，现在是他们3个，他们会冷静，然后
都没生气，就是我帮忙到这个是。哦，最近大家算到1万，
今天2-3个是这样，
慢慢涨，慢慢涨。
因为收益的是在收益在这边嘛，对不对？
也可以，但是
还是这个直接刚才帮他拿着讲，所以我就帮他切过来这里。对啊，这个这样今天这样就好了。
好，就是他100没起来。 Well, basically, okay, now we should start our last talk today. So, all right, so this talk will be given by Dr. Tu. She's just got her PhD in the University of Chicago and going to do a postdoc in MIT. So she's an expert of field theory, application, like mathematical physics, and today she's going to tell us, so you can see. So let's give the time to Dr. Tu.
谢谢大家今天留到最后一个 talk， 然后也谢谢organizer 给我这个机会在这边演讲。So I would like to thank for the organizer for giving me this opportunity to speak here, and for organizing this wonderful summer school. So as you can see, I would like to talk to you today is about the topic called nonlinear polarization of Fermi and non-Fermi liquid. Can people in the back hear me? Okay, great. So, okay, now better. So, I would like to tell you about this nonlinear polarization topic, which will be based on the work that we published a while back. And also today I will be focusing on some work in progress. So because of this talk will be a little bit technical, so please interrupt me at any time if you want to have some discussion or questions. Okay, so before I jump into the main subject of this talk, let me tell you what this talk is about and why this topic is so exciting. So as you can see here, there's some configuration that showed here, which is called the Fermi surfaces. And the physical system with this Fermi surface is usually with the gapless basis that described by, for example, the Fermi liquid or non-Fermi liquid theory, for example. So usually people are familiar with the theory to describe this Fermi liquid theory is described by a great physicist, Landau, a long time ago. It's called Fermi liquid theory. But we know that the Fermi liquid theory is not a field theory to begin with. So which gives a motivation why we want to study of this field of the quantum field theory description to understand the system with Fermi surfaces. So for this talk, I will be focusing on mainly on Fermi liquid theory But I will also give you some highlight of how this formalism can be also applied to non-Fermi liquid theory. I guess several speakers have been telling you in this summer school, like Chongho and Songzek, about this non-Fermi liquid theory. So later on, I will show you how this formalism can be also be very useful for describing non-Fermi liquid. Okay, so the goal of this talk will be trying to build up a quantum field theory to describe a system with the Fermi surfaces, like the configuration you can see here. And there are several approaches that we can build this field theory description. So I would like to focusing on this something called coherent state approach, which is some work we are thinking about in progress. Okay, so people might wonder why this formalism is so exciting and give us some benefits to understand some physical properties. So there are two main properties I would like to highlight in this talk. First is that you can use this formalism to calculate linear and non-linear responses. Okay. So what about this? Let's say you can see from the configuration here, there are some nonlinear responses, for example, like density occurring 3-point function, for example. So in the usual fermionics time, like you can see for the one loop diagram here, that usually people want to compute this nonlinear response, they need to compute a very long and tedious calculation of the loop diagram. But amazingly, we realized that in our formalism, we only need this tree-level diagram to compute those nonlinear responses. And we realized that the result actually match to each other. So this formalism, one benefit of this formalism is that it will reduce the calculation of this very tedious calculation dramatically. Let me give you a flavor how this calculation can be reduced dramatically. For example, like in the old literature, this loop calculation, it takes like 50 to 60 pages. But in our calculation, we only need 2 or 3 pages in our paper. And another thing that I want to highlight is that this formalism can also let us understand better about non-Fermi liquid theory, as I will tell you later on in this talk. Let's also have the property of this Fermi surface, but the transport and thermodynamic property will be different from Fermi liquid theory. Okay, so let me tell you what's the building block in the physical system of this talk, which is a system with the Fermi surfaces. And what is Fermi surfaces? Before we talk about this, let's do some thought experiment. Let's imagine there's a box here. And now what we're going to do is that we want to put some fermion into this box. So we know that the state of this box can be described by some wave functions. And now what we're going to do is that we want to put more and more fermion into this box. And we know there's by Pauli exclusion principle and thermodynamic limit, the system will form a system with the Fermi surface, as you can see the blue object here. So the entire talk, what we're going to discuss is a system with the Fermi surface, that you can see here. And we might ask the questions, what are those physical systems with a Fermi surface? Let's say usually with the system about the scaleless basis with a Fermi surface, for example, you can talk about Fermi and non-Fermi liquid. So the example of this is that we can thinking about something called conventional methods, unconventional method, or half-field Landau levels is the system that with Fermi surface. Okay.
What is I mean, it looks like the next paths wrong.
So I want to emphasize in that there are several types of bases on method. For example, you can talk about some gapless bases or with the gap bases. So I want to tell you that the emphasizing that our system is with the gapless bases. So this is something I want to highlight. Yeah, good. Any other questions? Okay, I will continue. So as I told you that we want to talk about the system that with the Fermi surface. So one of the example of that is the Fermi liquid. And what are the successes to the Fermi liquid theory? For example, those systems ranging from condensed matter system to high energy and astrophysical systems. So for example, like in the condensed matter systems, system of the conventional metal or liquid helium-3, and amazingly, also in a high energy and astrophysical system, for example, like the neutron stars, you also have some Fermi liquid, and also in the white dwarf. So I want to tell you that the formalism I will be describing today, although we are in the condensed matter systems, but also this formalism can be useful, we believe. It turns out to be useful for those high energy and astrophysical systems. So because of the time limitation, let me be focusing on this conventional method today. So we know that the Fermi liquid theory is described by this great physicist Ludwig-Landau in the 90s. It's the theory called the Landau's Fermi liquid theory. So what is Landau's Fermi liquid theory? It's a theory of the Landau's quasiparticles. And we know that the Landau's Fermi liquid theory is not the field theory. So which means that the Landau's Fermi liquid theory can be described by something called the kinetic equation. And why we say it's not the field theory, it's because that although it's described by this kinetic equation, and also we can use this kinetic equation to compute the linear and nonlinear responses, as you can see later on in this talk. But all these formalism are all to the leading order in momentum. So which means that we know that when we are talking about some field theory, we want to talk about all the orders of fields and derivative in combination of those. So what we're going to do today is that we want to build a field theory description to describe this Fermi liquid theory. And what are the benefits of that formulation? Is that it might help us to understand better about this non-Fermi liquid, as we will be telling you later on in this talk. Okay, so let me summarize what we're going to do. With the physical system that we want to describe is the physical system that with this Fermi surface. And what we're going to do is that we want to build up the quantum field theory for the system with this Fermi surface. So as I tell you that we aim to write down some local effective field theory for Fermi liquid in some bosonic degree of freedom. But people might wonder, what is the effective field theory? Well, so it's described of the this physical system on a particular energy and length scale and based on some general principles. Okay, so as I tell you, I want to build up a formalism to describe this Fermi liquid first. So what we're going to do now is that we want to formulate this Fermi liquid theory as some droplet evolution. So before I jump into the main subject, let me ask a question now. So what is the state of this Fermi liquid? Well, as you can see here, the state of the Fermi liquid is described by the closed Fermi surface in phase space with some arbitrary shape and volume. So how can one illustrate this object? Let's say we can thinking about there is some liquid droplet and with some arbitrary shape, like water droplet with some arbitrary shape, and we're putting in the this phase space. So this configuration can tell us a particular state of this Fermi liquid. So here I give you some examples how we can thinking about the Fermi liquid state. And we know there is some important property because we put this liquid droplet in phase space. And we know that the phase space has some canonical commutation relation here. So which means that if you quantize the system, that we can think about this phase space as some non-commutative space, which means that the droplet that you can thinking about is living in non-commutative space. Exactly. So the droplet is the blue object here. You can thinking about this blue object as some, for example, we want to visualize it better. Let's imagine there is some water droplet liquid that lives in phase space. Yeah, good. So here give you some different shape of the droplet, given the different state of this Fermi liquid.
We say a living boundary.
Yes, so this droplet tells you the configuration of the different state. Yeah.
So this droplet
no, it's okay. So let me put it in this way. So I want to build up the theory with the Fermi liquid theory. So now I will need to have the complete set of the state of different state of this Fermi theory. So what I trying to say here is that each of the water droplets it represents one state of the Fermi liquid theory. So for example, like what we mentioned is that different configuration, different shape, it represent different state of the Fermi liquid. Good.
Precise complex cells describe the system.
Exactly. So we want to write down all the possible states to represent the theory. Yeah.
So it's a manual.
It's I try to list, they give you some 3 of the examples. What are the different states of this Fermi liquid? Yes, right. Sorry, I didn't hear you. Exactly. Exactly. So I didn't tell you anything. I just list some possible state here. But if you want to make your life difficult, that you can talk about arbitrary state. But let's keep the formalism a little bit more simple here, so you can see. Yeah, that's a good question. Thank you. Any other question or comment before I jump into the next subject? Please. Sorry, I really cannot hear.
Can we have more?
Okay, so you are talking about, can we have some disjoint from research? For example, you have two readings. That's a very good question. So actually, we can list all the possibilities. But I believe that formalism, we haven't thought about that actually. So yeah, this is a question, open question. Okay, very good. Let me continue. So now we know that the state of the fermi-liquid theory can be figured as some water shape, as some illustration, and living in phase space or non-commutative space. So, what is the quantum field theory in non-commutative space? That's why we want to give you some fancy idea of this notion of the non-commutative field theory. And what is non-commutative field theory? Well, it's quantum field theory on non-commutative space, as you can see here. And for the non-commutative field theory, there's two important properties. Let me list down now. One of that is something called the Moyal product. For example, if you choose two given function, and the Moyal product tells you all the encoded or the higher derivative expansion. And another important property is called the Moyal bracket. As you can see, it has two curly brackets here. And it contains the notion of this Moyal product. And there another important property I will be using later on in this talk is that actually this curly Moyal bracket, as you can see here, will be reduced to the usual bracket in leading order in some parameter data. So how can we think about this data? It's usually can think about it related to the F-form that we have with. Okay, great. So the Poisson bracket of to the given function is defined here. And we know that in the leading order of the parameter expansion, this Moyal structure will be related to the Poisson structure. This is a very important property I'll be using later on when I want to reduce the relation of the quantum field theory to some semi-classical limit.
It's the real space.
Yes, so it tells you that this space is not coming. This is the property of this non-commutative field. So
I can list it X.
Very good. You are reaching out a very important question actually. So as you can see in the previous slides, there's some commutation relation of S and P. So actually, we pay the price thinking about there's some extra that the S and P not outside the code. So that's the price that you pay, but it's the same thing.
Okay. So some of the X is actually
exactly. Yeah, you are reaching the very important properties. Very good. You can thinking about as some parameter. It's actually has a name non-commutative parameter. So you encode it with the expansion. Like if you write it term by term, then you can see there's actually the non-commutative parameter expansion. So that it encodes some properties. Okay, Good. So let me continue. So why non-commutativity is so important? So actually, this formalism of building up the field theory description of this system with the Fermi surface has many kinds of different approaches. But why we want to add the notion of non-commutativity? Actually, it provides us a systemic formalism of the quantum field theory action of the Fermi surface. And it's a little bit apart from our previous paper that it has a new perspective of the nonlinear organization. And also we realize that there's some quantum version of the object. And because we are talking about the quantum version of that, so imagine we have a system with the Fermi surface. So if we access the quantum world, then this surface actually enters some uncertainty principle. So it will give you some fuzziness of the property from this non-commutativity, actually. Like what we mentioned previously, that actually this non-commutativity give you the higher order of the derivative, included by the parameter data. So it also gives us the non-analytic fraction from this non-commutativity. Okay, so now I'm going to tell you only based on the semi-classical approximation. We are not going to tell you about activity before it enters. So what about if we firstly make our library simple? Like let's imagine this simple convex spherical shape of the configuration. And we want to ask a question now. So what about the time evolution of this droplet? And what is the equation of motion that governs the time evolution of this configuration? So it turns out that the configuration change of the equation of motion of that is actually governed by the kinetic equation in a semi-classical approximation. And the structure of this kinetic equation is with this Poisson bracket structure of phase space here. So how can we think about this? Well, if we reduce our system to a more simple system, let's say we have a single particle system. And what is the time evolution of this single particle? Actually, it's governed by the Hamiltonian evolution. What can we think about this droplet system? Well, it's a system with a group of those particles. So we can imagine we have some domain that with all the particles domain of the group of the particle. And we want to understand the time evolution of the group of those particles. Which turns out that we realize that the time evolution of this particle is actually governed by the canonical transformation. Okay. So now, what is the dynamic of this droplet? Okay. So when we are thinking about the system, firstly, we want to choose the configuration this droplet. And we know there's some important property before when I told you about Fermi theory. We realized that there's some distribution function f, as you can see here, that inside this Fermi surface is actually the distribution function is 1, and outside of that is 0. So when we are talking about one configuration of this droplet in phase space, we can actually choosing the configuration, choose a phase space volume. So what is the phase space volume? So as we can see here, the configuration, here it defines the phase space volume of you need to integrate over the space. And all the structure is based on semi-classical limit. Okay. And because we know that the particle number is conserved, which is a very important property in our system. So which means that if you choose a given configuration of this droplet, and on the time evolution, actually we need to talk about the volume of this phase space conserved. Okay, so up to now, I tell you about the semi-classical approximation. Let me emphasize it. So for example, you choose a given Fermi state, and there's some phase space distribution function. Okay? And inside that, the Fermi surface is 1, and outside of that is 0. So in the previous case that we told you about this semi-classical approximation, and what about the quantum version of that? Actually, the Poisson structure that we see in the previous slides will be upgraded to some structure of the Moyar structure here. So this is something called the quantum kinetic equation. And if we expand it, like in the previous thing when I introduced the notion of this non-quantitative field theory, I tell you that the Moyar bracket will be reduced to Poisson bracket in the leading order in the province. So which means that now, if you take the semi-classical approximation, the droplet, if you want to talk about this droplet shape evolution on the time evolution, is actually governed by the kinetic equation that we are very familiar with. Okay, so let me zoom in and tell you what is this kinetic equation. So actually, this is the very familiar Ludwig's equation of free fermions that we know. And if we expand it, this Poisson structure will actually give you the Ludwig equation. And there's one important property I want to emphasize. That is that, remember, we introduced the phase space distribution function of the quasi particle. We mentioned that inside the Fermi surface is 1, and outside of that is 0. So this condition is preserved under time. Okay. So from this kinetic equation, I want to emphasize the usefulness of that. One of the things that we can compute, why I want to emphasize in this is that later on, I will show you we can actually, from our systemic formalism, we can also compute the linear and nonlinear response from our formalism. Okay, so from the kinetic theory, if we expand the fluctuation in terms of background, we can compute, for example, like the linear responses, and also compute the nonlinear responses from this kinetic. Good. Any other questions before I jump into the next topic? Okay, good. So in the previous slides, I told you the building block of this talk is the system with the Fermi surface. And I also tell you the time evolution of this Fermi surface is governed by the kinetic equation, for the quantum kinetic equation, the previous slides. And what I'm going to tell you now is actually the main subject of this formalism, which is that we try to build up the quantum field theory to describe the system with the Fermi surfaces. So there are several approaches of this. Let me give you one example of the coherent state half integral approach. Before I tell you about this formalism, let me review the first attempt trying to build up the effective field theory of this Fermi liquid. So all this great work back to long time ago, back to 90s, that people are trying to build up the effective field theory of fermions, treating this Landau's Fermi liquid theory. So in their work, that they want to think about this Fermi surface and divide it into patches. So, but there's some thing that we are not quite satisfied for the whole work. It's because that, for example, when I tell you I want to compute the nonlinear responses, there's some very tedious loop diagram that I need to compute. Sometimes when I want to compute those diagrams, there's some canceling between those diagrams, and will make our life very difficult. So there's an unnatural cancellation between those tedious diagrams that we are trying to avoid the perturbation theory. Okay, so this gives us another motivation why we want to study Vogelization. So what is Vogelization? For example, in the previous document, in 1+1 dimension, we know that fermions is dual bosons, 1+1 dimension. And in the higher dimensional Vogelization, all these great people, they try to generalize upon the higher than 1+1 dimension. And in those kind of systems that we want to thinking about, there's some higher boson at each point of the Fermi surface. So let me give you some illustration how we can think about that. So for example, in the two spectral dimensions, let's imagine there's some Fermi surface in 2D. And what is the is that actually you can thinking about this two-dimensional system as infinitesimal number of 1+1 dimensional system. Okay, so it becomes the infinitesimal number of 1+1 dimensional system. And at each point, there's some higher bosons of the Fermi surface. Okay. But there's some confusion also in this approach. Which is what is the general rules of formulating the action? So this is the question that we want to answer, and also the motivation of this talk. Okay. So this is the some thinking work in progress that we are thinking about. So we want to build up some coherent state approach to build up quantum field theory action. So what is coherent state? You can be thinking about as the deformation of the droplet. So if we consider there's some Fermi liquid state as arbitrary shape, this Fermi liquid state, and this gives you the coherent state representation here. And there's some building block of this coherent state, as you can see here. Some generators. And what can we think about this generator? So you can think about that there's some fermion bilinear, some particle pair, and we illustrate here as the generator here. And we know that this hidden structure, actually, it gives us there is some Lie algebra as well. So this Lie algebra, actually, we can check is the algebra that related to this Moya bracket, or it has another name called W infinity algebra. So which means that if you build up some given function based on the phase space function and also the generator, and you will satisfy relation of this the algebra as the Moya algebra. But let me not go too far. Question? In the previous slides? Okay, good. This is for the total field. So, yes. Oh, so yeah, good. So for example, in one plus one dimension, there's some left and right. That's just the label of that. Thank you for asking. Yeah, good. So, yes, exactly, very good. Okay. So this is the previous attempt, and what we're going to do now is that we want to build up the.
It's very like the
Okay, very good. So this just gives you some flavor of what one be. Yeah.
So I think that very well.
Exactly. Very good. Yeah. Any other questions? Okay. So I tells you that we can build up some coherent state as the deformation of this droplet of our coherent state mapping approaches. Okay, but all this will also one can ask. So what is the semi-classical approximation of this coherent state integral approach? So actually, this will reduce to our old paper. It's called the co-joint orbit method, which is building up upon the semi-classical approximation of this work. So if we take the semi-classical approximation, we use the property again that we that is reducing the Moya bracket to Poisson bracket. So now that the algebraic structure becomes the Poisson algebra, or you can tell you this is something called W infinity algebra. So what is cojoint orbit in our paper? It's some mathematical notion, but let me not go too far. So what is cojoint orbit? Let's say we choose some initial configuration of the Fermi liquid state. You can choose whatever configuration you like. And later on, we will want to perform all the possible canonical transformation. So all the possible canonical transformation will give you all the possible state with respect to the original reference state. So all the possible space of this Fermi surface state obtained by the group of canonical transformation, this will form the cojoint orbit. Okay? So what I mean by that is actually this cojoint orbit. It tells you all the possible space of the Fermi liquid state. So if you remember that previously I told you that what is the dynamic of this droplet, right? So actually the dynamic of this droplet can be occurs on this cojoint orbit because all the possible state is captured by the cojoint orbit. And also that the one given configuration of the droplet tells you one possible state of the Fermi surface state. So which means that each of the possible state is a point on this co-joint orbit as well. Any question?
The space of the state.
Oh, sorry, I didn't hear you actually. Okay, good. So actually, I'm very glad that you asked. So actually, that the Moya structure that you can see on the previous case here, actually, if you expanded the parameter data that you mentioned, that actually by using the semi-classical approximation, you can reduce the structure of the Moya structure to the source structure. That's how we can use that. It's close. It's close. So like here, you can see, you can check actually close. Please.
The element.
Exactly. That's a very important problem. Yeah.
The space of one will overcome this same number.
I think that's a very important question. I think if you want to make it complete, that probably you need to add this Fermi object as well, because this, as you can see in the previous slides, the algebra is actually made by the fermion bilinear. Yeah, I think this is a very important part. That's something I want you to think more.
What is the object?
So, okay, very good. So actually, we can thinking about there's you can check actually, and actually something called the W-infinity algebra.
Yeah. Right. Just mapping the this problem elements to the other.
Okay. So very good. So actually, if you plug in this relation, I think this will help you understand to answer your question. So if you plug in this relation and check the commutator of this operator, actually it gives you another operator and with the more structure. One can check on this algebra. But there's some higher level from commutative relation. I don't want to go too far. Give you some flavor of that. Very good.
What are Moya like FT below?
Okay, so this is the Moya bracket. You still remember that I told you that this is the function. To give a function f and g.
And this bracket.
This is the Moya bracket. This true curly bracket. This entire object is something called Moya bracket. Yeah. That's a very good question. So actually, my question is that this Moya structure will be reduced to the structure in the leading order data. Yes, but if you want to consider the high order, actually it's all encoded, all the possible expansion is encoded in this structure. And I think this is the answer. This entire structure actually is closed. Here, algebra is closed. Any other questions or comments? Okay, Yeah, please.
Writing with the space.
You mean this?
Yeah, writing.
Oh, okay. So actually, you can write it in moment and space as well. It depends on the notion. Yeah, this actually is all related to each other. Very good. But I want to emphasize this because starting from this big structure. Yeah. Okay. No further question. Let me continue. So what is the coherent state interpretation of this Fermi surface? So a state is actually an expectation value of the fermion bilinear. And we know that it can tells us what's the ground state and the state. And we realized that actually the ground state and the state are related to each other through this relation. And here is the Moya product that we realized previously. And also this can be, you can get this relation, something more like a Moya extension of the unitary transformation. So actually we can get this relation also from the quantum kinetic equation as well. Okay. So I want to emphasize in that actually here we have redundancy. You will bring the this Fermi surface state to the original state. So which means that the space of the state has some coset. And we can eliminate those redundancy or ambiguity, which means that we can choose a gauge phasing condition and reduce choose this gauge phasing condition is one of the gauge phasing conditions that we choose. And where we know that the scalar field is actually depends on S and theta. Theta is the angular direction. So up to now, we can finally very happy and related the theta here as a scalar field and do some the Fermi surface, as you can see here. So finally, it has some physical relation. And in a semi-classical approximation, we can do the similar thing and write down the ground state and also the state as well. Okay, so here is the main result of this paper and this work in progress. So what is the action of this homomorphism? So we'll answer this question by saying that the action will actually contains two parts. So this is the action, and we write down. So it contains two parts. The first term is the Wiener-Witten term. And how can we understand the first term? Well, there are several understandings we can think about. The first understanding is that it's related to something called the barrier phase. So imagine we have some configuration. And under the changing of its shape, you pick up some additive phase, which is universal fixed. If you try to add an interaction, you will not change this term. So this will relate to the first term of this Wiener-Witten term. And here, the barrier phase term, you can actually thinking about it as a state and carry some additive activity around the path in the closed space. And the second part is the usual Hamiltonian term that we are very familiar with. We know that it's an effective field theory, so we should be able to write down all the possible terms within the lambda function. So all these terms are hidden in this dot. Okay, So I tell you that the quantum field theory of the turbulent liquid it contains the two parts: the back phase with this term, and also the second term of this Hamiltonian term. Okay, so this is the end result of the paper. Okay, but I show you how we building up the formula, but I haven't wrote down the effective field theory action of this. So what is the effective field theory action that of the Fermi surface? Let me just give you some semi-classical picture of that. But as a quantum field theory, you can write down all the possibilities. But due to the limitation of time, I'm not doing this today. So in the Gaussian level, this is the result of the action. So this is the Gaussian theory, where phi here is the boson field, and n theta it tells you the unit vector along the radial direction of the Fermi surface. So in this does look something very familiar. Actually, it's just exactly the same as the multidimensional bosonization work, like in the previous work. So what can we thinking about? Actually, as I told you, we can, for example, in the true spatial dimension, we can reduce to the infinitesimal number of one dimension system. So this is located here. So which means that we can thinking about there's some chiral boson that's in the Fermi surface up to this Gaussian level. And we can also compute the density operator or the two-point correlation function and over. Okay.
他那边应该
Okay, so I'm very glad that you're finally lecture now. So let me actually. Okay, let me emphasize it very quickly. I hope I have some time. So let me emphasize the most important and interesting part of this talk, where is that we try to build out something beyond the usual multidimensional vocalization. Is that we need to compute based on the nonlinear field corrections. And before I tell you what those correction is, I want to answer where is the nonlinearities comes from. Actually, it comes from two parts. One part is from the geometry of the Fermi surface. So if you see here, the Wessel-Million-Witten term, for example, in this 1 over Pf, Pf is the Fermi momentum. It tells you the Fermi surface curvature. And another term here, you can see the object. The end data is the unit vector along the radial direction of this Fermi surface. So the zeta derivative of that tells you something about the extrinsic curvature. Another term I want to highlight, which is very interesting term, and you can see from this nonlinear correction, where you have the this nearby boson will actually talk to each other in this nonlinear correction, where you have the data derivative of this phi field captured in this nonlinear correction. And the second nonlinearity, it comes from the contribution of this Hamiltonian term. For example, you can actually, it's captured from the dispersion nonlinearity. So it can tell you there's some dispersion, nonlinear dispersion relation, and which can be captured for the nonlinear correction of this field. Okay. And another thing I want to highlight from the formalism is actually very important. As you can see here, it's this theory can make our life simpler from calculating the nonlinear responses. So, for example, in the O-fermionic side, I want to consider the nonlinear response here. You need to compute the diagrams. And we realize that it actually matched to the tree-level diagram on the bosonic side, and it will reduce calculation dramatically. And we checked that the matching, which is quite non-trivial, that the result will actually match to each other. And if you still remember, in the very beginning of this talk, I tell you that we can actually compute those nonlinear responses from the kinetic theory. And you can also check that the result that we get from the tree-level diagram, this is the bosonic result that we can get. Here, it's actually also matched to the old kinetic theory calculation as well. So, which means that from the fermionic side and bosonic side and the kinetic side, all the results were actually the same. The same. And because our result is in arbitrary dimensions, so in 1+1 dimension, all the Lottinger liquid action with Schumacher boson can also be captured. So I told you that in this section, what's the our effective field theory action will look like in the semi-classical approximation, and also tell you that it contains the nonlinear correction. Where does it come from? And I also highlight this formalism will reduce the computation of this diagrams. Okay, so in the formalism, I tell you we haven't switching on the gauge field. So let me now switching on the gauge field and tell you another direction relation. How can we use this formalism to understand? So how can one switching on and couple to the gauge field? It's through some gauging here. Because we mentioning that the Fermi surface is actually living in phase space, which means that if we want to couple to the gauge field, we need to couple to the gauge field of the phase space, as you can see here. And through this gauging procedure, that we need to treat the gauge transformation as a subgroup of canonical transformation. And we also know that the phase space is as some non-commutative space, like we mentioned previously. So which means that the gauge field that we need to couple is coupling to the non-commutative gauge field. And also that we know that the gauge transformation, because it's a non-commutative gauge field, so which means that the gauge transformation non-mobility, as you can see here, gauge transformation. Those two. But we want to understand the real fields. For example, there's some open question of how can we actually switching on the electromagnetic field in the presence of the baryon convection. This is something that is I'm actively thinking about now. Okay, and there's some relation to the LU1 anomaly, as you can see here. But due to time limitation, I think I'm not going to skip this part. But you can see that our relation can be related to this LU1, something called LU1 anomaly. Okay. Yes. I'm happy to discuss with you later on. Okay, so let me highlight one of the important things that formalism can be applied to. It's called non-Fermion liquid method or strange method. As we also hear about several beautiful talks in this summer school. So what is the non-Fermion liquid method? So actually, this non-Fermion liquid is also the system also have the Fermi surface, but the this thermodynamic and the transport quantity is not like the conventional method. And in the experimental side, you can see there's some high TC superconductor, a strength of crude rate. But in the theoretical side, that you want to consider there's some Fermi surface, but you need to couple the critical boson pH fields. So there are several models that we wrote on based on this, try to attack non-Fermion liquid. So let me just give you one of those examples. So now we can, this is action how it look like. And we couple the bosonic effective field theory action to some gauge fields. And we realized that in the tree level, we call that exponent of z equal to 3. The magnetic field is lambda depth. And we also know that there is some something beyond the tree level. For example, for this work previously, they try to compute this very tedious loop diagram. And if you still remember, I tell you that our formalism can be useful to understand non-Fermion liquid. So for example, in this very tedious loop diagram, you can reduce the loop calculation into some effective tree-level verticality. So which will reduce the calculation dramatically. I'm not going to tell you detail here due to the time limitation. And also you can, one might ask, so if we want to understand, for example, spectral Fermi surface or the BCS theory, for example, and what can we do about that? Well, so you need to understand by consider the extension of the algebra to include. Okay. Let me skip this here. And also, our formalism can also include Barry structure as well from the modified bracket. Okay, let me give you some conclusions. So we want to build up effective quantum field theory action to understand the system with the Fermi surface. And there are several approaches that we can use to understand, build up the systemic formalism. So I give you one of the example, which is the coherent state path integral, and build up a systemic formalism for the nonlinear effective action of this Fermi surface. So from there, this approach, a state of the Fermi surface can be equal to some droplet on the commutative base. And we know that the algebra is the algebra with the Moya bracket. In the semi-classical approximation, it becomes the Poisson algebra. And we successfully built up the nonlinear bosonic effective field reaction at arbitrary dimension. And also, there's some benefits we can use this formalism is to reproduce the linear and nonlinear responses in the more neater way. And this formalism can also be very useful to understand better about Fermi liquid. The wish list I want to share with you. One thing is that the non-Fermion liquid theory extension, for example, you approach the critical gauge fields, or there's Moya bracket generalization, because the effective field theory I share with you today mainly focusing on dynamic classical approximation. So in the we can use this Moya bracket generalization, for example, to understand better about this 2K physics, BCS, analytic fraction, or you might want to consider permanent plus this, and they are a lot more bigger. So, am I talking? Thank you very much. No, I believe that people talk about this local one anomaly. You can see this beautiful paper by Santo and friends back to 20. So what's the concept of this local one is that actually, for example, we can think about some 2D Fermi surface, and I tell you that can be reduced to the infinitesimal number 1 plus 1. So in each of this one dimension system, you can think about this one once. So now it becomes the of the concept I told you. Yeah, this is actually I'm very glad that you answered this question. It's a very important properties that we need to check the effective field reaction, the equation of motion, the loop. Yeah, we can check that.
And also, similar equation, I don't think going to be
Yeah. Yeah, that's a very good question. So actually, there's a subtlety I didn't be too clear in the previous due to time limitation. So actually, we have this data derivative because we do some gauge basing and to fix all the magnitude of this momentum, and we only keep the zeta change. So we encoded all the momentum derivative, the zeta. Exactly. So you have the Fermi surface and theta is probably the angular patterns. Yeah. Thank you. Any other questions or comments?
Question from the online audience.
Didn't see any.
So let's take some. Yeah, let's go.